Okay. Good morning, everybody. Thank you very much for being in this session. Today and tomorrow it will be our sessions or our mini colloquium on Fermi surface topological transition and interaction effects. My name is Joseph Beturas from Loughborough University. I will be chairing this session. Co-chair is Pablo Rodriguez Lopez from Madrid. And Edwin Herrera will be our, he will assist us on any kind of technical issues and questions we might have. I would like to ask you to use the chat for questions. It looks that, I mean, there are many people, so if there are manageable number of questions, I will ask everyone to pose a question. Otherwise, I can read from the chat the question, and then the speaker will have the opportunity to answer. I mean, I'm sure that it will be a very lively, as much as possible, lively and very good, excellent session. And without further delays, let me ask Amalia Coldea from Oxford University to start her talk about iron selenium. Thank you very much.
Thank you very much, and good morning, everybody. It's a great pleasure to be here with you through this medium. So today I will talk about the electronic signatures of the nematic electronic phases in a family of iron-selenium compounds, which are isoelectronically substituted with sulfur. So, oh dear. So the plan of my talk is split in a few parts. So first of all, I'm going to discuss the ARPES studies on iron-selenium and how they allow us to visualize the features of the nematic phases in these compounds. These results are based on different work published in the last few years. And I acknowledge all my collaborators who've been part of the studies. Secondly, I will look at the quantum oscillations and what we learned about the quasi-particle effective masses. And follow on from there, I will discuss the nature of the nematic critical point in these materials and how it differs from other critical points found in other systems, in particular iron-based superconductors. And in the last part, I will look into the magnetotransport and in high magnetic fields and what features and how they manifest in the systems due to the likely anisotropic scattering which may be present in these nematic phases. So first of all, in iron-based superconductor, we have intertwined electronic orders, in particular the nematic and magnetic orders are the two contenders competing for providing the pair for the superconducting state. This is a generic phase diagram of an iron-based superconductor where we have a tetragonal phase in the high temperature. Then as you cool down, the system goes through a structural transition, and often some of the materials become magnetically ordered in a counting antiferromagnetic phase. So here it's the representation of the Uniaxial, a high temperature. You have the tetragonal Uniaxial A and B are equal, but as you enter the structural transition, the A and B become non-equal, so you break the rotational symmetry of the system, and at low temperature, the magnetic spins with a very small moment can order in a collinear antiferromagnetic states where you have ferromagnetic chains antiferromagnetically aligned with each other. So now also the issue about superconductivity is if at the end of these phases, we might recover quantum critical points, and if this superconducting phase, which is stabilized, has anything to do with criticality. So as you can see here, we could have two potential contenders, one coming from a nematic critical point and the second one coming from a magnetic critical point. So all the physics of these materials relates to these ion planes, which are bonded to a chalcogen or pictogen, which sits above the plane, and ion usually sits inside of the octahedra. So now the nature of this structure transition before the system becomes magnetic it's under a lot of debate, because we can have a few different potential candidates. First of all, it could be that the lattice plays an important role, and we have a tetragonal to orthorhombic transition due to the interaction with the lattice. But the studies of transport and isotropy show a very large difference between A and B direction, much larger than one could predict based on the changes in the lattice parameters. The second candidate relates to the orbital degrees of freedom. The fact that in the tetragonal phase we have two degenerate orbital states, dxz and dyz, and as one goes through the transition, this degeneracy is lifted, and then we can develop a certain polarization due to the orbital degrees of freedom, which determine the occupation of different bands. So here we have the Hall bands at the gamma point and the electron bands at the X point in this representation. And as you go through these transitions, you expect that these pockets will distort and their orbital occupancy will change. Obviously, another reason the same effects could occur in a magnetic channel, and the susceptibility along different direction could be different and drive the transition, the structure transition. And lastly, one can also think that a Fermi liquid in the presence of interaction could distort this Fermi surface from in this case, isotropic Fermi surface to a very elongated Fermi surface. These ideas were proposed a long time ago by Pomeranchuk, and often this is called Pomeranchuk instability, which is a deformation of the Fermi surface. My mouse doesn't work. Can't change the slide. Okay, sorry. Here we go. So today I will discuss the phase diagram of iron, selenium, sulfur, and what's unique about this family is that it does not contain the magnetically ordered state. So here we have a unique opportunity to investigate the nematic electronic phase in the absence of magnetism. Magnetism is present in form of very wide dispersion fluctuations which extend from a low energy to very high energy, but there is no stabilization of magnetic orders, and such we do not expect any kind of reconstructions of the Fermi surface. Furthermore, if we look in the phase diagram here on the left, we have the position of the structure transition and superconductivity. All these are obtained from measuring resistivity versus temperature. And here we have the kink at about 90 degrees for iron selenium, and as we add sulfur, this transition is further suppressed. So in a crystallographic way, the sulfur and selenium occupy position, as I said, outside the ion plane, which determines all the electronic properties. And often how far away this ion is very influential on electronic structure. So as sulfur is smaller than selenium, we also refer to this way of substitution, which is isoelectronic. That means we do not dope with electrons or holes. We refer to this way of doping as a chemical pressure substitution. So this phase diagram is quite unique, as I said, because it does not contain any magnetic phase. We have the nematic phase suppressed with sulfur substitution to about 17%. There is a tiny dome of superconductivity inside, but there is no enhancement at the nematic endpoint here, and then there's a slow decay of the superconductivity, which survives all the way to the end compound. So this is in contrast to what happens under applied pressure, where similarly one can see a nematic phase and a small dome of superconductivity for small pressure, but pressurizing further, the spin density wave at the magnet is destabilized. So it's living somewhere in the vicinity of this nematic phase, and together with this spin density wave, the superconductivity is enhanced a factor 4. So it's clear that magnetism has to play a role in enhancing the superconductivity in iron selenium under pressure, though no signature is seen with sulfur substitution. And by combining both chemical and applied pressure, we can see that we can tune these phases, and we can reveal the position of the nematic critical points. And here, I will show some data where we look at the pressure for the 12.7 compounds, and we look at what happens in these places, both with sulfur substitution, but also with applied pressure. So here are the first study I'm going to discuss. It's ARPES studies. And as I mentioned before, the structural details are always important in determining the electronic structure of these materials. We have a multi-band system. These are compensated semimetals. So the whole bands live at the center of the Brillouin zone and are two-dimensional cylinders, and the electron bands live at the corner of the Brillouin zone. Comparing iron selenium and iron sulfur, from the band structure point of view, we can notice that the differences are quite subtle, and the number of holes vary, being only 2 for iron sulfur, but predicted to be 3 of them for iron selenium. What changes significantly between these two systems is actually the z-axis value, suggesting that we can expect certain warping effects as we move across the series. And here are a summary of results in iron selenium and what we learned from it. So what we know in ARPES, it's quite a unique technique, because by using light polarization, we can probe the different orbitals. So in a particular cut, we can be more sensitive to the one type of orbitals. So this Fermi surfaces shows how the orbital configuration varies as we go around the Fermi surface. So you can have, this is at the trigonal phase, a mixture of dxz and dyz orbitals. And for the electron bands, we can expect also to have the dyz orbitals. Now, in experiments, despite the predicted Fermi surfaces of iron selenium to have 3 whole bands, in experiments at high temperature, we only recover 1 single cylinder and a very small 3-dimensional Fermi surface centered at the Z point. Furthermore, the studies have allowed us to determine the binary normalization factors associated with the different orbital characters. And here is an example of, actually, these are the points extracted from the data, high temperature. So these are the band dispersions for the different colors correspond to the different orbital characters. This is in a tetragonal phase. And we have alpha band, the outer whole band, and then we have the beta band, the inner whole band. And the renormalization for these 2 bands with mixed dxz and dyz character is about 3 to 4. Whereas for the other whole band, which was supposed to cross the Fermi level in calculation, is pushed about 50 milli-electron volts below the Fermi level. And this is due to the very strong band renormalization effects of about factor 8 or 9, which makes this system quite unique when we think about orbital differentiations and what role they play. As we enter the nematic state, the effects we see are quite striking. We can see that these two bands, it's almost like they repel each other. One of them shifts up and the other one shifts down. And these are the effects to do with orbital effects, band shifts associated with the transition into the nematic phase. And while these band shifts occur, then the Fermi surface changes from an isotropic circular Fermi surface to a very elongated elliptical Fermi surface. And the small little pocket which was present at the Z point disappears completely at low temperature. So these are the generic aspects that one would expect to happen inside the nematic phase, and this is exactly how we expect the nematicity to manifest as a direct elongation of the Fermi surface and consequently affecting the transport and potentially developing anisotropic scattering in this configuration. So to further understand the difference between the hole bands and electron bands, this is a very good representation of those effects. So as I said before, as you break the symmetry from this tetragonal symmetry where you have the general dxz and yz state, these two bands will shift, and then we also have a dxy band very present in many of these pockets, in particular for the electron pockets. So we expect that for the gamma band, as I discussed before, we already have an effect to do with spin-orbit coupling, which is about 15 electron volts. But as we turn on the nematicity, this band will shift. And then for the electron bands, the effects are even more dramatic because besides lifting the degeneracies of XZ and YZ band, we have further anisotropy to do with the dxy orbital and their hopping anisotropy. And they will cause extra shifts. These points are supposed to be degenerate in the tetragonal phase, but turning these effects on, the bands will shift in an unusual way. And these are some simulation of how these effects might occur. And here at the top are the simulation for the hole bands, where I put some realistic number from experiments on the tetragonal system. As we turn, this is only turning the spin orbit coupling on. We have a finite band splitting for the hole bands, but increasing the nematic effects. These shifts will occur. One band keeps shifting down, and then the inner hole pocket will disappear. Whereas for the electron bands, they are a bit more unusual because they are formed of two crosses ellipses, and we have these two degenerate points. But in the presence of spin-orbit coupling, this degeneracy is lifted, and then turning on the nematicity, we can see how this pockets start distorting, squeezing the inner electron band, as you can see, as this dispersion is touching the Fermi level. And eventually, if these effects are pushed further and further, some topological changes could occur for the electron bands, and this can disappear altogether, and two little pockets could be left for very, very strong nematic effects. So these are the qualitative trends that we could expect in experiments, and we look at the system starting both having materials in the tetragonal phase, but also how these changes occur in the nematic phase. And here are a summary of our results. These are the ARPES data and the high symmetry cuts along the diagonal of the unicell. And these are the two bands I discussed initially, alpha and beta, and at about 50 milli-electron volts, we have this highly renormalized dxy band, which is present for all the different concentration. So the Z and the gamma point have slightly different dispersions because we have a corrugated cylinder, but the general form in these pictures are pretty similar, and hardly any changes are visible. But more striking is the effect at the end point. As I discussed, we have now here we are expecting two dispersions. The outer one is supposed to be dxy character, but because of its very strong renormalization effects and becoming more incoherent, is much harder to observe in experiment. Just a little shoulder is seen in this momentum-dependent cuts. So this shoulder are tiny visible, but more striking is under this band as we turn on the pneumaticity, so going from the right to left, these 2 points split, and this effects of band shifting becomes very significant, reaching a value of about 50 milli-electron volts. And we can take cuts in the Fermi surface, and again, what we can see that the tetragonal phase has this isotropic Fermi surface as we expect, and as the system goes towards low temperature, towards the iron selenium end here, then this Fermi keeps distorting, and in the iron selenium case, due to the presence of two domains, we can see two cross ellipses. Similarly here for the electron bands, we can see that this is what one predicts to happen, to have this two crosses ellipse. Indeed, these points will be separated by the spin orbit coupling, but it's very hard to resolve here. And as we turn on the effect of pneumaticity, these bands become more elongated, and there's still a strong debate if this is the two ellipses or a single ellipse still remains here, and we'll hear later more from Luke on the effect of strain on the systems as well. But these materials have very strong Kz dispersions, and as you can see, at about 12%, the pocket is recovered, and the Fermi surface of iron selenium at high temperature is kind of recover as we turn off the effect of pneumaticity, and we have a Fermi surface containing a whole band, but also a three-dimensional little carrier, which plays a role in transport. So this is the summary of what we see in experiments, that the effect of pneumaticity shifts the bands by about 30 milli-electron volts, and that there we have a very strong Fermi surface distortion. These are cuts for how much of the Kf value for the electron pockets, and here we look at the relative elongation of these pockets in relation to their tetragonal case. And we can see that this elongation of the Fermi surface is suppressed at about 18%, which is where pneumaticity disappears. So this is a direct evidence of the existence of the pneumatic phase and how it changes. Furthermore, in the systems, the correlations also change with sulfur substitution. So these are electron bands dispersion for iron selenium in the tetragonal phase, and also for 18% compound in the tetragonal phase, compared with iron sulfur, which is the right end member of these compounds. And we can see how the bandwidth increases, and also the velocities associated with the hole and electron bands significantly increases. That means the system becomes more metallic and less correlated as we go towards the sulfur end. I mean, I only have a few minutes left, so I will probably go quickly through what we learned from quantum oscillations. So quantum oscillations obviously is about a probe compared with ARPES. And here we measure transport, so we expect that the resistance to be dominated by the most mobile carriers, because the system can be thought as a parallel net of resistance with the different contributions from different bands. So what we learn in quantum oscillations is that from about 12%, so this is the concentration for which the new three-dimensional little carrier appears, we see a very slow frequency developing, and that frequency survives all the way to the nematic transition and then disappears. And this effect was somehow unusual because in ARPES we know that the small three-dimensional pocket is supposed to be there, but it is not supposed to go away because it's found also for 18%. So it's almost as if there is another transition happening exactly at the nematic endpoint, which could have a different origin from what we see in ARPES. And so we think that this is potentially a Lifshitz transition where you can think that one of the cylinders becomes extremely distorted by chemical pressure, so the warping increases, and at some point it loses the center of this band and the orbit is gone. And the same effect happens with chemical pressure, but also with applied pressure. So here with applied pressure, we again tune across the nematic phase from about 0, 4.7 is about close to the critical pressure. And again, we have a very slow frequency here, but that slow frequency is gone outside the nematic phase. And it's represented by this lambda pocket and the frequency versus pressure phase diagram. Most of the frequency increase with pressure or chemical pressure, but this particular one seems to disappear at the nematic phase transition. And we look back at the ARPES data to try to see if there are clues about where they might come from. And one potential origin of this anomaly is the fact that for 18% concentration just outside the nematic phase, we can see that the whole band is highly touching the Fermi level. So we only have about, within the resolution, just 3 milletron volts, suggesting that this band is pushed well down, but obviously still present at the Z point. So one explanation is that indeed this transition which we see in quantum oscillation could either be due to the Lifshitz transition induced by chemical and applied pressure, where the orbit at the gamma point disappears, or potentially be induced by applied magnetic field, because we have very small bands, and in magnetic field one can polarize up and down these bands and lead to this disappearance of this point. And one more point about the effective masses in the systems. So as compared with other system, here the effective masses have a very small increase inside the nematic phase before they decrease. Probably it's better represented in this graph where the effective mass for the dominant orbit, which is the outer whole band orbit, the Z point, decreases in this way, which follows what happens to TC. So TC has a small enhancement inside the nematic phase before decreases at the nematic endpoint. And this lack of divergence at the nematic endpoint is quite unusual because one we expect in a system with antiferromagnetic, the antiferromagnetic critical point to have a very strong divergence. This is the case of barium-122, so you can see the effective mass increase significantly divergent towards this critical point, and also TC increases significantly in that particular case, whereas in this family, the effects are more subtle, there's hardly any change in TC, and the effective mass do not show divergence either. And this also occurs under pressure. Similarly, we follow very carefully what really happens to the nematic endpoint, and the changes are very subtle, very small variation in the effective masses and the coefficient from the transport. So there's no divergence. The masses are heavier inside the nematic phase and they decrease outside. So we lose, the nematic phase is a correlated electronic phase and no divergent electronic correlation are found to the nematic endpoint. And we suggested that this potentially could be a manifestation of the quenching of the critical fluctuation along certain direction because of the finite coupling between the electronic system and the lattice. So this nematoelastic coupling, this is a phase diagram of what could happen in the presence of the nematoelastic coupling, that we can also expect that the system will have non-Fermi liquid behavior at high temperature before it becomes a Fermi liquid. And this is what we detect with pressure, this transition from to Fermi liquid behavior at low temperature, which allows us to estimate what that coupling could mean and how that coupling could also lead to the shifting of the phase diagram and the position of its critical point. But because in quantum oscillation we measure orbitally average mass, and if the criticality is only allowed along certain direction because of this coupling, then an average effect will not show any divergent correlation at the nematic endpoint. And this type of coupling also has significant effect on the transport properties. And this here I represent how the N coefficient varies with temperature. And these are with the studies under pressure, which we see that exponent of about 3/2 is maintained for quite a large range at high temperature. But there is a variation in the exponent, and this type of variation in the resistivity exponent has been suggested to be a signature of the interaction of the system with acoustic phonons, so interaction with the lattice. And here again, I show you that at the nematic endpoint, we do not have linear T resistivity, but indeed, both with chemical pressure and applied pressure over a very large temperature range, we recover a dependence which looks like 1.5 or 3/2 dependence in the vicinity of the nematic endpoint. Also, in both cases, you can see that the superconductivity is not enhanced. It's clear something significantly affects this critical fluctuation because they are strongly suppressed. And this, again, has been discussed in a recent paper by Labat and Paul, that in the presence of a weak coupling with elasticity, one expects the nematic fluctuation to be enhanced and to have a domal superconductivity in the vicinity of the nematic critical point. But when this coupling is strong, that enhancement is suppressed, and also we might expect that the pairing to be dominated by non-nematic interactions. So do I have any more time?
Probably 1 more minute to wrap up, 1 or 2 minutes.
Okay,
and then, yeah.
All right, so in transport, as I mentioned, we do find unusual behavior. This is also in high magnetic fields inside the nematic phase. There's significant magnetoresistance developing for the system which are nematic compared with the B² depends as expected outside in the tetragonal phase. And this change is also in magnetotransport seem to be correlated with the changes in the Fermi surface. In particular, the appearance of this 3D pocket causes this change in slope in high magnetic fields. This is in 34 Tesla, and also the sign change of the Hall effect. As I said, transport is unusual. We see a regime of linear dependence all the way to low temperature, but then Fermi liquid kicks in at the lowest temperature. And this linear temperature dependence is inside the nematic phase and seems to correlate with the presence of spin fluctuation. So it's clearly inside where we have the distortion of the Fermi surface. Spin fluctuation are also likely to play a role, in particular anisotropic type of scattering effects. And the magnetoresistance seems to have a usual power law, which may again suggest that a signature of this unusual scattering. And the way we might think of it is that when we have very distorted Fermi surfaces, then we could have hot spots and variation in the velocity along all these pockets, and they will contribute in an unusual fashion, giving rise to this type of temperature dependence for the Hall effect, which is close to what is seen in experiments. Okay, to summarize, so we have done lots of studies to try to understand the electronic behavior and the manifestation in this family of compounds. They are an ideal set of materials because they are clean. We can tune them, we can cleave them in situ for ARPES. They show very strong Fermi surface distortion and band shifts because of the kinematic orbitally dependent effects. We have small changes and presence of a new little three-dimensional pocket, which seems to be important for transport behavior in this multi-band system. And there are no divergent fluctuations at the kinematic endpoint, suggesting that something else suppresses both this fluctuation and superconductivity, and one of the potential reasons could be the magnetoelastic coupling. And what we found in high magnetic field studies is that the transport is anomalous inside the kinematic phase. There is a regional linear T, but we find a very extended T/3/2 close to the kinematic endpoint, and where the spin fluctuation may be present. Well, thank you very much, and I'm looking forward to hear your questions.
Thank you very much for a very nice talk, Amalia. There are two questions so far. Could you please clarify about small frequency oscillations in B field? What is the B field direction, and is it a closed to open Fermi surface transition?
So we have performed angular dependence studies for all these compounds. So these measurements I show here, these are all the different composition for when B is parallel with a C-axis. Because in this particular compounds, they are superconducting and upper critical field is extremely large. So we have here 15 Tesla, which goes to about 25, 30 Tesla. So to access the normal state, we need, this orientation is more favorable. And also indeed, when we do angular rotation, this quantum oscillation will disappear for about, I think above 40 Kelvin. So we expect that this pocket to emerge from a quasi-two-dimensional cylinder, so that it still is like a very elongated ellipse to have the properties of a quasi-two-dimensional features, but then we don't see it further than 40 degrees. So that's all we can say, that this pocket is likely to be this one, but we can only find quasi-two-dimensional signature up to the angles we measure.
Yeah. Thanks. That question came from Sergei Slizovsky. The next one from Ilya Remin is if the dxy outer electron pocket is missing in the measurements, how M* is then evaluated for the xy orbital?
So what we measure, so what I present, the masses here are for the whole band. So actually, let me go look here. So we do have, these are all the points we could measure and detect, and to follow the band we think we follow. So for low concentration, we can detect two different Fourier transform peaks coming from the gamma point, which is the dxy band, and it's heavier. So we have a mass of about 7, which slightly increases, but we can follow the delta band all the way. So we can't say too much about the dxy band, what happens to it, but in quantum oscillation, if something is heavier, it's harder to observe. We also think at some point these orbits are becoming quite similar, so it's very hard to really reveal the behavior of the dxy band from quantum oscillations because of all this constraint due to its heavier mass and because it's very close proximity to the delta band.
So if I may still ask, because I see that I can unmute myself, Amalia, So does it mean that if you don't see it in the ARPES, you claim that you actually see this gamma band, this outer electron pocket in the quantum oscillation?
So based on the effective mass of this band, which is about 7, we think that's how we assign this particular pockets to the DXY band. So obviously that's how we assign it. Okay. Based on its mass, because it's much heavier than the other one.
But from the frequency, you can in principle estimate also the size of the pocket, but this you cannot really say.
So the size of the pocket, obviously we do it from a different, in a different way. You do it from the angular dependence. It's done here. Okay. So here this is the gamma pocket is done here. And then you have to think about charge compensation, because it's our compensated system, how many electrons and how many holes you have to keep the charge compensated.
Okay.
Thanks. So Clifford Hicks is asking, is the disappearance of the small electron pocket at Z as iron selenide is cooled into the nematic phase an important driver of electronic properties of FESE?
So for a system like iron selenium sulfur system, we have these are multiband systems. So the physics of multiband system is dominated by small pockets with high mobilities. So what we know that, for example, this whole like carrier here has a very light mass. Also from ARPES, we know that this has a much higher velocities. So that means that it's going to dominate the transport. And the way how it affects, which it's in particular we can see in magnetotransport. So for example, you see very large magnetoresistance, we see very low temperature, but also in the Hall coefficient. And the whole effect, the whole component in the magnetic field is very unusual. So what we know, for a compensating metal, again, you would expect to have almost no Hall coefficient in a multiband case. But here below the transition, so 87 is the transition in iron selenium, you can see this negative Hall coefficient strongly developing. So we think that this is to do either that a highly mobile electron is present, because a 3-band model is required to understand this data in magnetic fields, or some other anisotropic effects occur. But as this little pocket at 11% shows up, we can see that the Hall coefficient changes sign. So clearly, this small little speckle of carriers, both electrons and holes, are very important in understanding the magnetotransport behavior of these compounds. So we can't just simplify to a 2-band system. They do start playing a role, and we notice changes. For example, here, when the slope of the resistivity in 34 Tesla really changes exactly the point where this 3D pocket seems to appear.
Thanks. And the very last question from Rosa Valenti. In the evolution of the DXY band at gamma upon S substitution, is it going from more to less correlated system?
So because we expect that towards iron sulfur it's a much better metal. The mass enhancement is only a factor 2. We expect that all the bands to become less correlated as we go from iron selenium towards iron sulfur.
So Amalia, sorry, writing was a little bit difficult what I meant. So the point is, as you already said, there is a big discussion on the position of this DXY band, and it is really much below the Fermi level in iron selenium as you would get in any calculation, even including correlations. Now, one is arguing that this band is strongly correlated. So my question is, when you go and dope with sulfur, where is the position of this band in your ARPES? Where do you see that it's shifting up or it's staying similarly to what you see in iron sulfur? Because this question goes also with what Ilya was asking. You seem also in quantum oscillations to see some features of this DXY band. So what happens when you dope? Where is the position of this band, for instance, in ARPES?
So the position, so the ARPES, just before I go to ARPES, just again, so we see this evidence of this band here, just that it follows similar trends to the delta band. This is the whole outer orbit of the whole band, so this is the outer orbit of the electron band. So now when I think about these orbits, for me are these flower-shaped orbits. Okay, so this, and they contain some DXY character. Mm-hmm. So they are not pure DXY, as you would think in ARPES, but they contain, because we measure orbitally average orbits, they will have a bit of DXY character as you go around the Fermi surface. Now here, I mean, this is probably the best way to think about what happens in sulfur substitution. This is the 18% sample, which is just outside the nematic phase, so it's in the tetragonal phase, and you do have the two ellipses, exactly what you expect to have in the tetragonal phase. So obviously, if the ends of these two ellipses are the DXY parts, is there. And velocities, I mean, we cut, so you see the position, if you look, this is where the shoulder is for the DXY band. It's much harder to see, but that's what you expect those positions to be. And in a way, you could think about the system like what happens in iron selenium at a high temperature. And this is, in a way, what we see with sulfur, that we drive the system back to where it was before the nematicity turns on.
Okay, thank you.
Thank you very much. Great talk.
Thank you.
Let's move to the second invited speaker, Clifford Hicks. Uniaxial stress-induced Lifshitz transition in sodium ruthenate, the 214, the superconducting one. Clifford now at University of Birmingham and also at Max Planck in Dresden. Please.
Hey, well, thank you, Joe, for the introduction, and yeah, it's good to have the opportunity to talk to you this morning. I'm still physically located in the Max Planck Institute for Chemical Physics of Solids in Dresden. On paper, I've moved to the University of Birmingham, and I expect to move physically in January. So yes, I'm going to tell you about Lifshitz transitions in strontium ruthenate induced by uniaxial stress. So before, let's see, let me get my laser pointer. So before talking about strontium ruthenate, I was going to tell you a bit about some old experiments done about 40 years ago on Lifshitz transitions in conventional metals. So the experiment here is an experiment applying tension to filaments of aluminum. So these are whiskers with a width of a few microns and a length of a few millimeters. And it turns out that when the transverse direction is very small, you can get far higher elastic strains than you would in a macroscopic piece of aluminum. So the data on the left show the change in resistance against the elongation of the sample. And they can stretch these samples by almost 2% elastically. And what we see is if they look at 25 Kelvin, there's a little anomaly in the resistivity at an elongation of about 0.5%. The change in the resistivity is small, it's well under 1%, but it's there. And now if they look at TC, the TC of unstressed aluminum is 1.2 Kelvin, and at the same point, an elongation of about 0.5%, there's a little anomaly in TC with a scale of about 20 millikelvin. In the thermopower, they can see clear quantum oscillations. So at 0.18 GPa, that is about here, about 0.2% elongation, they see a relatively fast oscillation frequency. At 0.27 GPa, this is slowed down. At 0.37 GPa, we're looking at this larger oscillation here. That frequency has got smaller, and at 0.4 GPa, it is extremely small. So what's going on is shown here. So these are the Fermi surfaces of aluminum, and the stress direction, the direction along which they're applying stress, is the 110 direction here. And the key thing that's going on is these necks here and here. Those necks are becoming narrower and eventually break, and that's the Lifshitz transition that drives these little anomalies. A similar experiment was done on rhenium. So this is rhenium under hydrostatic stress, and its TC initially has this stress linear decrease, but then starting at about half a GPa, there's an anomalous increase in TC, and that is also associated with a Lifshitz transition. The scale of the change is tiny. TC drops and then goes back up by something on the order of 10 millikelvin, less than 1% of the unstressed TC. Okay, so now to talk about strontium ruthenate. So this is the lattice structure of strontium ruthenate. It contains ruthenium oxide sheets separated by strontium oxide spacer layers. And the conduction occurs within the ruthenium oxide sheets. So it is a highly two-dimensional material. And we're going to be applying stress along the 100 direction along the ruthenium oxide bond direction. This is what the essential experimental setup looks like. The sample is a relatively long and thin bar, and its ends are embedded in epoxy. It's very important that the ends are not clamped. They're embedded in epoxy, and that provides a conformal layer that avoids points of stress concentration. And that lets us reach very high stresses with very high stress homogeneity. And here's a picture of a sample mounted on a stress cell. This cell is almost 50 millimeters in diameter. It has piezoelectric actuators which drive motion of this block of titanium here. If we move this to the right, that compresses the sample, and then the force from the sample is applied to this block, and these titanium bars here and here, there are 4 in total, those bend slightly, and there's a capacitive sensor behind it that measures how much. In effect, that operates as a force sensor, so we can measure the force that is applied to this sample. Right, and here are some data. So this is the percent change in the resistivity from the unstressed value, starting here at 0 GPa. Negative values of stress denote compression, so we're compressing the sample in this direction, and at about 0.7 GPa, the resistivity of these two samples at 5 Kelvin is enhanced by almost 40% from the resistivity of unstressed strontium ruthenate. So there's a much, much stronger response than in the conventional metals, rhenium and aluminium. I think even more striking than that is when we go beyond this Lifshitz transition, we see this very strong decrease in the resistivity to well below values seen at 0 stress. So we know well that strontium ruthenate is an unconventional metal at 0 stress, that it has strong electronic correlations. I think that what we're seeing is that these correlations are then strengthened as we reach the Van Hoff singularity, but then are very rapidly suppressed as we go beyond it, and strontium ruthenate seems to become a much more conventional metal at very high stresses. That is a general theme along which we're still working. On the right-hand side, I'll show you how this peak washes out with temperature. At 10 Kelvin, it is still quite sharp. 15 Kelvin, it's noticeably broader, and at 35 Kelvin, it is largely faded away. Here's how the superconducting critical temperature evolves. Starts at 1.5 Kelvin and then reaches a peak at over 3.5 Kelvin. In other words, TC more than doubles. Once again, a much more dramatic effect than in the conventional metals. So the differences between strontium ruthenate and aluminum, one of them is that strontium ruthenate is simply a much more strongly correlated metal. but the other one is that it has a nearly two-dimensional electronic structure. And so with the three-dimensional metals, at the Lifshitz transition itself, you have a divergent local density of states, but the total density of states does not diverge. When you have a Lifshitz transition of a two-dimensional metal, you do have an actual divergence in the total density of states. So a much stronger anomaly in the density of states and much stronger effects. So to show concretely what happens, these are the Fermi surfaces of strontium ruthenate. This is from very high resolution photo emission data from the Baumberger group at the University of Geneva. We have two electron-like Fermi surfaces, the beta Fermi surface and the gamma Fermi surface, and then one hole-like Fermi surface, this alpha pocket in the corners. Quantum oscillation data show that there's a modest mass enhancement. The masses on the alpha and the beta sheets are enhanced by about a factor of 3 from bare band calculations, and of the gamma sheet by a factor of 5.5. To emphasize just how two-dimensional this material is, I show here the out-of-plane versus the in-plane resistivity, and the resistivity ratio is about a factor of 1,000. So this here is rho C, and that is measured in units of milliohm centimeters. This curve here is rho AB, and that's measured in units of microhm centimeters. For both of them, we see t-squared dependence, Fermi liquid behavior, below a temperature of about 20 Kelvin, and that corresponds well with the temperature scale on which this peak in resistivity at the Lifshitz transition fades away. So, the fact that the Lifshitz transition is caused by the gamma sheet under uniaxial stress, this distorts elliptically and it touches the Brillouin zone boundary at a single point. It can also be manipulated with doping. So here's some work before we started our uniaxial stress measurements. So this is substitution with lanthanum. Lanthanum dopes electrons into the system. So that expands the electron-like Fermi surfaces. And we see that the gamma sheet here touches the zone boundary at a lanthanum content of about 0.27. The heat capacity, the Sommerfeld coefficient, increases as lanthanum is substituted into the system and reaches a peak at about 0.2. So in other words, at a lanthanum content of about 0.2, the electronic heat capacity is at its maximum. This is about where this transition occurs. Similar work has been done by the group of Kyle Shen at Cornell. So this is approaching this Lifshitz transition through epitaxial strain. So here is bulk strontium ruthenate. There are some extra Fermi surfaces visible due to surface reconstruction, but the key one is here. This is the gamma sheet, and we can see that we're well short of the Lifshitz transition. When the lattice constant is expanded by growing it on a strontium titanate substrate, we're now much closer. When they switch to barium ruthenate, which for thin films has nearly the same electronic structure, they are right at the Lifshitz transition. And now when they expand the lattice constant further, they have clearly gone beyond it. So if we look at, when they look at transport properties, this is the resistivity as a fraction of its value at 45 Kelvin versus temperature. All of these films show good approximately t-squared resistivity, except for this one, the barium ruthenate on strontium titanate. This one right here, that has a power law of about t to the 1.4. So going to this, approaching this Lifshitz transition affects the transport properties quite strongly. Under uniaxial stress, we achieve a Lifshitz transition in a different way. As I told you before, the gamma sheet distorts elliptically and eventually touches the Brillouin zone boundary here. So this is ARPES work, first on unstressed strontium ruthenate at the top, and then coming down, this is photo emission data on a sample that has been compressed along the x direction by about 0.5%. This was done using differential thermal contraction. So this Lifshitz transition here corresponds to the peak in resistivity. So here's resistivity data now going to very high stresses, about 2 GPa, And we can see, again, this very strong decrease in resistivity that saturates, brings the resistivity down to about half of its unstressed value. My colleague Stuart Brown at UCLA has done NMR work on strontium ruthenate. So this is the essential measurement geometry. He's applying field in this direction, and that gives gives 3 inequivalent oxygen sites. We have this one which sits between these ruthenium sites, and that direction is aligned with the field direction. And we have this oxygen site that sits between these rutheniums, and that axis is perpendicular to the field direction. These drawings here show the relevant oxygen p orbital. For this oxygen, that p orbital is perpendicular to the applied field. So when the applied field polarizes the electron cloud, that gives us a little polarization like this, and that dipole field produces a field in the opposite direction at the nucleus. So that means that the night shift of this nucleus, the field at the nucleus in comparison with the applied field, is negative. The nucleus sees a field slightly less than the applied field. These oxygens, it's opposite. The p orbital is aligned with the field, so when they polarize, their dipole fields create a field that is aligned with the applied field. It sees a positive night shift. Right, so this is what Stuart Brown's group sees as a function of applied strain. So these are our 3 oxygen peaks. This is the frequency shift. This is the NMR frequency shift. This one here is this parallel site with the negative night shift. This peak here is the perpendicular site with positive night shift. And as they strain the sample, what they see is that the night shift of this peak increases and reaches a maximum at this string here, right at the Lifshitz transition. It's a little bit harder to see for the apical oxygen sites, but as a fraction of the frequency shift, they see the same enhancement. And from this, they extract that the spin susceptibility at the Lifshitz transition is about double what it is in unstressed strontium ruthenate. Okay, so now I want to talk about the superconductivity. So strontium ruthenate, as I've told you already, is a superconductor, and it's very clearly an unconventional superconductor. So its TC is extremely sensitive to the residual resistivity. A very small concentration of defect suppresses the superconductivity completely. That means it is an unconventional superconductor. It has, in addition, a curve rotation, a small but definite curve rotation of about 60 nanoradians at low temperature, and then as temperature is raised, this curve rotation disappears at Tc, and that indicates that the superconducting order parameter has a rotational sense. It is chiral. So what do the strain data tell us? Data under uniaxial stress show a very strong enhancement in the upper critical field that gives a strong indication that the superconductivity has even parity. So at the left, I showed the data for field applied along the C-axis. In unstressed strontium ruthenate, the upper critical field is below 0.1 Tesla. It's quite small. When we tune it to the Lifshitz transition, the upper critical field is right about 1.5 as T goes to 0. That is an enhancement of a factor of about 20. The important quantity to look at is Hc2 over Tc squared. If you take a superconductor and you scale the gap without changing anything else in the electronic structure, then Hc2 over Tc squared remains constant. What we see as we go to the Lifshitz transition is that this quantity is enhanced by a factor of about 4. And what that means is that a large gap coincides with a small Fermi velocity more than in unstressed strontium ruthenate. That's highly suggestive because when we tune to this Lifshitz transition, the place where the Fermi velocity is smallest is right at this point, right at the Van Hove point. So this very strong enhancement in Hc2 tells us that we have a large superconducting gap right around this point. Now, the thing is that this point is parity invariant. This point is the same as this point on the opposite side of the Brillouin zone. It is a single Van Hove point. So if we had an odd parity order parameter, by symmetry, the gap of that order parameter would have to vanish at this point. So if we say that we have a large gap at this point, then it must be an even parity order parameter. Similarly, if we look at the in-plane HC2, that also gives strong evidence for even parity pairing. So the in-plane HC2 saturates at a little bit more than 4.5 Tesla at low temperature. Now this ratio, 4.5 Tesla to 1.5 Tesla, is much smaller than the intrinsic, than the band electronic anisotropy of strontium ruthenate. To get an idea of the orbital electronic anisotropy, we look at the slopes here, dHc2 by dt as we approach Tc. And the in-plane HC2 comes in almost vertically. So that says that the underlying electronic anisotropy is very strong. The orbital limited in-plane HC2 should be many tens of Tesla. Instead, we only see 4.5 Tesla, and we also see a very clearly first order superconducting transition. We see clear hysteresis between increasing and decreasing field sweeps. So this is an indication of Pauli limiting, and that only occurs, generally that occurs when the pairing is spin singlet and when the orbital order is even parity. And then there's been recent NMR evidence on unstressed strontium ruthenate that in unstressed strontium ruthenate, the order parameter is also even parity. So these again, the NMR intensity as a function of frequency. Here we have our, excuse me, parallel oxygen site, and here our perpendicular oxygen site. And what Stuart Brown's group did is they then plotted this as a function of pulse energy. And what they saw is that as the pulse energy is reduced, the night shift is reduced. So their interpretation is that this high pulse energy, that's enough to heat up the electron such that it is no longer superconducting. As they reduce the pulse energy, the electrons stay cold throughout the entire measurement, the sample stays superconducting, and they see a strong reduction in night shift. That is as expected for spin singlet pairing, where spin up must pair with spin down. Kenji Ishida from the University of Kyoto has also done this experiment. He was able to raise the temperature to above Tc. So here he shows night shift versus temperature, and there's a strong reduction in night shift as the sample becomes superconducting. So this leaves us with a conundrum for strontium ruthenate. And this is the central conundrum of the superconductivity of strontium ruthenate, is how do we reconcile chirality with even parity pairing? Under the tetragonal symmetry of strontium ruthenate, the natural candidate to consider is xz plus iyz. However, that has a horizontal line node at kz equals 0. And for a layered material, for a strongly two-dimensional metal, that is really not expected. That's very hard to explain. So how to reconcile even parity and chirality is the core mystery of strontium ruthenate. And so I just want to show you one more thing to finish my talk. And this is another mystery. So we can also approach this Lifshitz transition through c-axis stress. So I'll show here the orbital content of our Fermi surfaces. This gamma sheet is mostly composed of XY orbitals. It has a very strong XY character. Now, as we apply stress along the c-axis, we are restricting the space for the xz and the yz orbitals and increasing the space for the xy orbital. So this reduces the energy of the xy orbital. This Fermi surface expands to both Van Hove points simultaneously. My colleague Helge Rosner calculated that this should happen at a c-axis compression of about 2.5%. We should reach both of these points at the same time. So if we have an even parity order parameter and we can access both of these points where the density of states is extremely high at the same time, then presumably we're going to see a really dramatic enhancement of Tc. Maybe we even get our longed for room temperature superconductor. So this is what the experiment looks like. Here's our sample of strontium ruthenate. This is the c-axis. it has been shaped so that we reach very high stresses, and then we wrap coils around it to measure the magnetic susceptibility. I show you raw data here. This is the superconducting transition as we compress the sample. And now my final slide, I show you TC as a function of C-axis compression. My student Fabian Yerzenbeck, he was able to compress the sample by 2% elastically. And then what we see is that TC decreases. And that's a mystery. If we have an even parity order parameter, why should TC decrease as we are increasing the density of states? For proof that we are increasing the density of states, you can look at the upper critical field, and that is increasing as we apply this C-axis compression. So with that mystery, I finish my talk. Thank you for your attention. This work, many people have contributed to it. In the interest of time, I won't go through everybody, but I will highlight the contributions of Mark Barber, Alexander Stepkin, and Fabian Yerzenbeck, who did much of the hard labor of the measurements that I told you about. And thank you for your attention.
Thank you very much, Clifford, for a very, very nice talk. Please, questions.
I have a question, if I can ask in person.
Yes, please.
So my question is about the upper critical field and the superconducting gaps. So in this multi-band system, do you have a single gap? And why do you think the expectation for upper critical field should only be described by a gap if that's not the case?
You're asking, so I think what you're asking, we have multiple Fermi surfaces. Why should we care so much about that single point?
Yeah.
And the enhancement of the density of states at this one Lifshitz point. And I mean, I can't give an absolute 100% certain answer to that question. My colleague Thomas Gaffidi and Steve Simon have done weak coupling calculations for various order parameters, comparing even and odd parity order parameters. And they calculate the gap within this weak coupling model for all of the Fermi surfaces. And they confirm in their calculation that the even parity order parameters have this strong enhancement in HC2 over TC squared, while the odd parity order parameters do not. And I think this extreme rise in HC2 as well. So I guess my less sophisticated view of it as an experimentalist is that this rise is really very extreme, and there's nowhere else in the electronic structure, there's nowhere else in the Fermi surfaces where something rapidly is changing at this Van Hove point. This change in shape of HC2 versus stress, in a conventional metal, HC2 versus temperature should have a convex form, the classic WHH form. Here we see this concave form, and we know from measurements that that's a change that occurs really very close to this Lifshitz transition. So that's something unusual that occurs right around this point, and that would prompt us to really look at the place in the Fermi surfaces where something is changing sharply.
Okay, thank you.
Next question.
So I have a question on the C-axis compression. So you left us now with an open question. So you basically compress your sample and your TC goes down. I mean, you were expecting to go up because you are reaching, in fact, these red points.
Right.
Now, which alternative explanations do you have for that? Or you are really now trying to find an explanation for that?
I literally have no idea.
Okay.
Okay, I mean for for 20 years, everyone thought for 20 years the dominant hypothesis for strontium ruthenate was that it was an odd parity superconductor, a chiral superconductor with px plus I py order. Now in weak coupling calculations, you tend to find D wave and P wave superconductor quite close. in energy. So as pure speculation, one possible, maybe under this strong c-axis pressure, maybe we do have a transition to odd parity order, and then an odd parity order parameter would really would not be favored by tuning to these Lifshitz points. That's very strange, though. You would tend to you would expect to tip it in favor of something that could take advantage of this very strong density of states.
But I thought that the recent NMR data from Stuart Brown, first of all, they clearly say it is an even parity superconductor. Right. He's now doing also measurements under this uniaxial strain. Are there results on that? Because if it has to do with this change of odd to even or even to odd, I mean, this is a very delicate type of change.
I wouldn't bet any money that that's what's going on. That's the best I could do. That's the best idea I can give you right now. Unstressed strontium ruthenate is almost certain to be even parity indeed. Yeah. So why under c-axis stress it should favor something which gives it a lower TC? No, that doesn't make sense. But that's
okay. But it's a nice open question. Thank you.
Herman, could you please ask your question?
Yes, thank you. Thank you for the nice talk. Yeah, so I just want to make the point that actually the pure strontium ruthenate has an extremely small upper critical field. It's nearly a type 1 superconductor, and this is quite a strange situation. So my question is, actually, I am not surprised that whatever you do, you increase the critical field. Now, could you present your last measurements where you show the resistivity? These ones, yes, the previous transparency. I wonder why it seems that the transition width increases when you increase your strain. So is this right? And I wonder what happens to the, I mean, there are very few defects in this sample. These are very pure systems usually. Right. But what happens with the defects when you apply strain? Do they move? And if they move, what would happen to the sample?
Almost certainly there's no motion of defects within the sample. I mean, we apply strain and we go back and we see that the behavior is elastic. If you apply high uniaxial stress to strontium ruthenate at room temperature, you do see introduction of dislocations, and you see motion of those dislocations. It deforms plastically above about 0.2 GPa. So it's crucial here that these stresses, we're only applying these stresses well below 10 Kelvin. So there's very little thermal energy for motion of defects. I mean, I can't tell you for certain that no defects are moving around, but I can tell you for certain that we don't see any large-scale plastic deformation of the sample.
And how do you explain the increase in the transition width?
So the TC is very sensitive to in-plane strain. So just to be clear on the data, so this is a susceptibility measurement actually. It's the mutual inductance of these coils. So we're measuring magnetic susceptibility. And right, so what you're asking about is this tail. We seem to see this tail of increasing TC. And I think this is just an extrinsic effect of in-plane strain. So we're compressing the sample along the c-axis by 2%, and we get this decrease in TC of about 0.1 Kelvin. Now, with an in-plane strain of 0.2%, 0.1 to 0.2%, we increase TC by more than this. So in other words, we have to apply the strain with quite high precision, so we get this 2% c-axis compression without a 0.1 or 0.2% in-plane strain. And I think you're seeing the sort of limits of the precision that we reached on that. This feature here, this tail here, does not reproduce in a second sample, but this decrease does. So I think that's the intrinsic response to c-axis strain. This is an artifact of some in-plane strain due to the sample bending or due to imperfections in the sample. We don't know exactly, but it's an artifact.
Thank you.
Any other question? Okay, thank you very much, Cliff. for a very, very nice talk. And
thank you.
let us, the next one is by Vadim Grinenko, again, on, it is S+is superconductivity triggered by topological changes of the Fermi surface in iron-based superconductor. Please.
Can you hear me?
Yes.
Okay, so as the chairman said that now I want to come back to iron-based superconductors, and I would like to present you one a new exotic superconducting state, so-called S+is superconducting state in a barium iron 2 arsenic 2 system doped by potassium. This work was done mostly in Dresden. Mostly done in Dresden in the group of my boss, Professor Hans-Henning Klaus. So he is here. So, and all MUSI experiments were performed in PSI Willigen with the great support of Hubertus Lütkens. Of course, all this work would be not possible with very high quality single crystals kindly provided by Chu Ho Lee. And we had a huge theoretical support from several groups, including Yair Roman, who is here today. And here I would like to especially emphasize Mikhail Silayev, who performed calculation of spontaneous currents in S+is superconductors. I would like to, since probably not everybody knows what is time reversal breaking superconductor, so I would like to give you some short introduction on the topic. So first of all, what is unconventional superconductors? So there are many definitions for unconventional superconductors, and maybe one of the most general is that the superconducting gap function should be momentum dependent. And this results to the fact that in addition to broken gauge symmetry, like in every superconducting states, in most of cases, we have an additional broken symmetry, such as the symmetry of the rotational symmetry of the crystalline lattice, like in D-wave cuprate superconductors, or it could be related to a spin part of the order parameter, like in non-unitary superconductors. And so what I would like to talk today, mostly it's about unitary superconductors and where the superconducting states break time reversal symmetry, so-called Z2 symmetry. So it's a very tiny fraction of superconductors which break time reversal symmetry. And it's accepted now, so that in this case, the order parameter should be a two-component order parameter. And this is a result of the frustration in the Buring interaction. And here we can consider, expect two possible cases. So the first case is a degenerate order parameter, like was already today presented by Cliff. So where the two components are equal, and the states are P plus IP, D plus ID, or F plus IF. And the phase diagram in this case is expected to be symmetrical with respect to any tuning parameter. On the other hand, for the non-degenerate order parameter, or in some cases accidentally generate order parameter, the order parameter consists of two different, in most of cases, different by symmetry appearing states. So that The simplest example is S plus IS, two different S components, S plus ID, G plus ID. And the phase diagram in this case is expected to be non-symmetrical respect of the tuning parameter. And so here is what the point where the TC can be equal to time reversal breaking transition is a special point. And it's require fine tuning to get this point. So therefore, in the mean field approximation is expected that the time reversals dome is usually below superconducting transition temperature. Now let's talk about our system. So barium iron 2 arsenic 2. It's again multi-band metal. The Fermi surface is similar what you already saw for iron selenium, but it has more sheets. So it's usually contains 2 or 3 Fermi pockets, whole Fermi pockets in the zone center, and 2 electron pockets in the zone corner. And it's already, I would say, widely accepted that the physics of this compound, especially in the without doping and at the optimum doping situation, can be understood in 2-band picture. So where the interaction between hole bands in the zone center and electron bands in the zone corner drives the magnetism and unconventional S plus minus superconductivity. And and what is important for our talk here, so that when we dope the system by holes, so in our case it's potassium, so this doping can drive the Lifshitz transition. So, and the Lifshitz transition in this case is that electron pocket at the M point moves above the Fermi level. And so then, of course, in this case, we have a problem with this standard S plus minus picture. So now let's look on the phase diagram for potassium doped barium iron 2 arsenic 2. So without doping, it's a spin density wave antiferromagnet with near temperature about 140 Kelvin. So when we dope this hole, so as magnetism is suppressed, and it gives room to superconductivity. And interesting here that superconducting dome is very large. So it's continuously extended up to the full substitution of the barium by potassium. And superconductivity survive over the Lifshitz transition, which I was talking on the slide before. And here is a more complex picture for the Fermi surface. And basically what happens, so this electron pockets disappears and it's replaced by another hole pockets. So let's come now to what is S plus IS superconductivity and how it can live on this complex electron Fermi surface. So let's come again back to the optimal doping. So when we have hole and electron pockets, so for the simplicity to understand this physics, we can consider only 3 pockets, and it will be sufficient for understanding the physics. So in this case, what we have, so as the interaction between hole and electron pockets drives this S plus minus superconductivity in 3-band model. So one can call it like S plus plus minus. So which means that you have same sign of the order parameter on the hole pockets and the phase of the order parameter on the electron pockets is rotated by pi. And this can be presented by this simple simple diagram. So then if we go to the situation where the electron pockets is disappeared, and so then of course the simplest solution can be that we have simple S plus plus, so that this phase doesn't change, but it was shown in several theoretical works, so that another type of interband interaction can drive S plus minus superconductivity. And in this case, the sign of the order parameter is changed between two hole pockets in the zone center. And then if we interpolate between these two cases exactly close to the Lifshitz transition, so then it's we can have the situation where the both interaction of the similar strengths and then the phase of the order parameter doesn't know what to do, and it's frustrated. So it has some arbitrary phase which is different from pi or 0, and this state is so-called S+is appearing states, and the state breaks time reversal symmetry. So the main consequences of the time reversal symmetry breaking, it's appearance of domains. So because this is why it's called the two phase transition. So and the domains can be viewed in this picture. So these domains is S+is or S-is. So and they are different by the way how the interband phase is changes between different pockets. Important for our study and that this domain walls so can have magnetic signatures. In particular for S+is superconductor, so the situation is rather complicated, but it definitely it's the end of the so that it was demonstrated theoretically that in the end of the domain walls one can have appearance of spontaneous magnetic fields when you cool down below the superconducting transition temperature. Another source of the spontaneous fields is defects in the sample. So and so here you can see the simulations of the field and current distribution in S+is and S-is state around spherical inhomogeneity. So the inhomogeneity in this state result in the gradients of the phase or amplitude, and these gradients are responsible for appearance of spontaneous currents and spontaneous fields. And if you can see, so that the differences between these two domains is that the fields are directed in different direction. And another important feature of the S+is state, which looks like is something specific for S+is state, is that the fields are mostly aligned in a AB plane. And this could be another, but I will use it like an experimental signature for this phase. So, and the anisotropy of these fields is quite large. So it's like, can reach up to 3 orders of magnitude and depends on the anisotropy of the Fermi velocities. So what we are looking for? Of course, this most well-known example is strontium ruthenate, and time reversal breaking superconductivity in this compound were discovered using mu-psi experiment, muon spin rotation experiments, where there was observed that muon spin relaxation rate enhances below the superconducting transition temperature. And this enhancement was related to appearance of additional fields, which are additional fields which caused by the superconducting state. Average value of these fields is, for this particular case, was estimated on the order of 1 Ørsted. So these fields can be even smaller. For example, some other example like strontium platinum arsenide has a similar behavior, so where this relaxation rate is enhanced below TC, but the amplitude of this enhancement is only fraction of Ørsted. So we are really looking for very tiny internal fields. So now I would like to talk a few words about our experimental setup. So experimental, so here is our muons, which go through the which goes to the sample, and using the two detector pairs, backward, forward, and up and down detectors, we can monitor not only the value of the relaxation rate, but also the direction of the fields in the sample. And the main complication for our study is that samples of barium iron 2 arsenic 2 are very tiny, very thin single crystals. So the average thickness of these crystals is about 10 microns, doping of interest. However, for the experiments, we need about 100 microns. And so it means that we need to stack a lot of crystals together, and every crystal must be checked. And so we shift in this experiment so that the doping varies between crystals only within 2%. So now our central result. So the central result is shown here. So, and what we see here, that relaxation rate is indeed enhanced below the superconducting transition for two doping levels. For other two, doping levels slightly above or slightly below, we didn't observe such kind of enhancement. So this enhancement we related with the appearance of spontaneous magnetic fields in the very narrow doping range. So, and the size of these fields is on the order of fraction of Gauss or Erskine, so similar to other superconductors with broken time reversal symmetry. And interesting, so which is really new for such kind of superconductors, is that the spontaneous fields are anisotropic. And we observe that indeed, so the clear relaxation rate enhancement was observed only for direction of the muon spin polarization along c-axis. So indicating that, and when for other directions, we could not find a change of the relaxation rate. And it indicating that if the fields, so these fields are aligned in the AB plane. So of course, it's important to search for other indication for this unconventional superconductivity and change of the pairing symmetry in this doping range. And so here I would like to show that how the specific heat changes across this doping level. And so we are, so this is a temperature dependence of specific heat for different doping levels in the superconducting state. So, and then, so if we plot the specific heat jump at TC, normalized by Sommerfeld coefficient and by temperature, we found that there are two characteristic scaling behavior. So the at low doping levels is well-known scaling behavior where this value varies roughly like TC squared, and this is so-called Nie-Budko-Canfield scaling, which holds for many iron peptides, and it's related to this unconventional S+- superconductivity. On the other hand, at higher doping level, we observed another scaling behavior, which is also indicates unconventional superconductivity in the system, and could be understood in terms of S+- superconductivity also, but since it's a very big difference between two scaling behaviors, so it's well, we expect that it's another type of S+- superconductivity. And this state, which with broken time reversal symmetry, is exactly observed in the region where the scaling changed from one to another. So finally, I would like to summarize our findings and present the phase diagram. So this is the temperature doping phase diagram, and the blue stars are superconducting critical temperature. So it superconducting critical temperature decreases with the doping above the optimal doping. So optimal doping somewhere here. So it goes down nearly linearly, and then abruptly changes around 60–70% of the doping, flattens, and in this range we observed time reversal symmetry breaking state. On the same time, so the Sommerfeld coefficient is nearly doping independent, down to this 65–70%, and then sharply increases and flattens at high doping levels. So the Sommerfeld coefficient can be, this behavior of Sommerfeld coefficient can be understood in terms of Lifshitz transition, which appears roughly around 60% of the doping. So, and here is DFT calculations of the Sommerfeld, of the density of state. And so one can see that in qualitative accord with the experimental data, Sommerfeld coefficient is nearly doping independent at low doping levels. So then has sharp maximum, which is not observed experiments, and then this behavior is reminds this behavior of the experimental Sommerfeld coefficient. So there are several reasons why this sharp peak may not be observed in the experimental data. One of the reasons that experimental Fermi surface is much more three-dimensional, is more three-dimensional than theoretical one. The second reason is that the measurements of the Sommerfeld coefficient performed at rather high temperatures, so above 20 Kelvin. And of course, this will smear out considerably the sharp anomaly. And the third one, of course, defects. So defects also will result in smearing. So however, all other paths, I would say, looks quite similar, which allows us to roughly relate this change in Sommerfeld and critical temperature to Lifshitz transition, which happens around 60%. In addition, so Ilya provided us calculations of the critical temperature using 4-band model. And one can see that the critical temperature also behaves similar with experimental one, so that it decreases and then change faster above the Lifshitz transition, and it has this spin density, it has this BTRS state roughly where this critical temperature flattens. So on the right side of the Lifshitz transition. So now I would like to conclude. So that we found the S+, presumably S+is state in the narrow doping range between 70 and 85% of potassium doping on the right side of the Lifshitz transition. And here is, I would like to emphasize that Lifshitz transition play important role in the changing the peering interaction in the system, and give the possibility to have this very exotic superconducting states with broken time reversal symmetry. So thank you for your attention.
Okay, thank you very much for a very clear talk. Please, any questions? I've got one about how do you get from, probably I missed it, but how do you get from the nodeless S plus minus to time reversal symmetry breaking? Is it continuous or first order or crossover? What is this type of?
Do you mean
Yes.
the transition between nodeless and nodal?
Yes.
So this, the nodal and nodeless is coming not from our studies. So that is, it's found in the ARPES and the penetration depth measurements. And the behavior is rather complex. So basically what happens here, so that nodes gradually appears. So it's not really, let's say it's not a transition, it's like a crossover, so that the gap is getting more and more anisotropic. and then in on the one Fermi surface, it is on the gamma point, so it appears nodes. Roughly at this doping level, so we have this Viteri state, and then above the Viteri state, the nodes appears on the other pockets. So in this sense, I would say that a Viteri state tries to close the nodes, at least on the some Fermi pockets, which is expected. So it's so which gives more energetically favorable this mixing of the two peering state to increase the condensation energy. Yeah, so I would say that the Viteri state exactly lives on this border where the node starts to appear.
Great, thank you very much. Yes, Amalia?
So I have a question concerning the impurities. What is the role of impurities on this state, and how fragile it is to impurities?
One need to understand two things. So one thing is that if you have the very clean system, ideal crystal, and it's has the S+is state, so it's infinitely large crystal. So then you would not have the magnetic signatures in this state. So it will be just a single domain, and there will be no spontaneous currents because this spontaneous currents appears on the Fermi surface in the K-space, and it could be shown theoretically that it always will be a compensation of these currents. So to visualize these currents, one need to do some imperfection. So and this, for example, if you have some inhomogeneities where you have a variation of the order parameter, phase, or the amplitude, this will result to appearance of these currents around these impurities. Of course, this is just local, so you have just weak separation of the order parameter. In this sense, you don't change the state. Of course, then the question, if you have a lot of impurities, what will happen? So, and then it depends again on the symmetry. So, of course, you have two different components. So one can speculate that maybe you can have a different suppression rate, so a different sensitivity to impurities for these two different components. And then you may split, so you may affect differently superconducting transition temperature, which of course will be given by the strongest component, and then this time reversal breaking symmetry. But we didn't do yet the systematic study, so I cannot tell. So we're now on the way of studying this.
And I have one more question. Would you expect to see signature of this with STM, with other probes as well?
Of course, there was, it's a very complex question. So probably you know that for strontium ruthenate, there was a similar study, not with STM, but with this scanning slit and scanning hole microscopes. And up to now, nobody really detects these spontaneous fields on the surface. And this is a big open question. So for some reason, there are no spontaneous currents on the surface, even for this classical example like strontium ruthenate or other ones. So for this reason, of course, for this particular compound, I don't know, so we didn't check, and this was not yet measured. But for others, it's a real puzzle. So this is a mystery, and so we are thinking about this kind of experiments. How to say, I would say that it could be that the surface is somehow different, and it's without the spontaneous.
Thank you.
Thank you very much. So let us now move to Hans-Henning Klaus from Dresden, who is going to tell us about the time reversal symmetry breaking superconductivity in back in strontium ruthenate 214 and how to manipulate it. Please. Yes.
Yes, hello. Can you hear me?
Yes.
Okay, great.
Could you please share your screen?
I would like to do so, but for some reason it doesn't work right now. The deactivation is not activated from the host so far. Now, thanks. Now I'm there. All right, can you see my screen?
Yes, perfect.
Fine. Okay, yeah, in my talk, I want to come back to strontium ruthenate. So, and mainly I will talk also about μSR on strontium ruthenate under uniaxial strain, going through the Lifshitz transition of the Fermi surface. So that's why I think it is a good talk also for this session. No, not everything works here. Why can't I switch my, 1 second, I cannot switch my slides. Now, okay. I will give a short introduction only to the unconverted superconductivity in strontium ruthenate. Mainly it's the question which I want to discuss is, do we see time reverse symmetry breaking at different temperatures than superconducting transition in the system? And some part of the question, the ideas why this is interesting has been already introduced by Vadim in the last talk. So then I will definitely discuss, yeah, what do we see in terms of μSR in strontium ruthenate, and will really tell you that indeed now with muons we have found the splitting of superconducting transition and the time reverse symmetry breaking transition. But in the study under uniaxial strain, we also went beyond the Van Hove singularity, and there we have found spin density wave magnetic order. And I will shortly discuss and continue the discussion by Cliff, what are the constraints on these results on the superconducting order parameter symmetry. Okay, and the collaborators, definitely Vadim, who has just given the talk, is a very important person. In addition to that, Srinanda worked on it. She's also here today, and she will also introduce a little bit more in the afternoon in a poster and short talk about the device. And of course, Clifford Hicks was very important to develop the device and take part in the measurement and give many ideas. And beyond that, there are several other people, of course, μSR people from PSI in Switzerland, where we did the measurement, and samples also came from Yoshi Maeno and from Naoki Kikugawa. Okay, the introduction can be very short. I want to talk about the time reversibility symmetry breaking. So that essentially can only occur if we have somehow degenerated order parameters, superconducting order parameters. So in the case of strontium ruthenate, it could be px and py states because we have the tetragonal lattice structure. And already in 1995, 1 year after the discovery of superconductivity in strontium ruthenate, Siegrist and Reis came up with the idea that these two degenerated states indeed can form a coherent two-component orbital state in the sense of px plus or minus ipy, because that state then avoids nodal lines in the 2D gap function. So basically a p state or a d state, of course, has nodes, and which means there is no condensation energy at this part of the Fermi surface. And if you combine it in a coherent state, then we can gain more condensation energy. And of course, if we have the situation, then we can have a plus or a minus here, and that will give rise to chiral domains. So it's considered this state as a as a topological superconductor, because you can have domain walls, you can have some surface currents, and so on. So important for the μSR and for any technique to measure the time reverse symmetry breaking is what Vadim also mentioned, that at surfaces or impurities or at these domain walls, spontaneous currents can form, and this will give rise to the static internal magnetic fields, which we detect by μSR. And yeah, the old data were already shown by Vadim in the last talk. On strontium ruthenate, the first data were from Graham Luke and co-workers in 1998, where they clearly see an increase of a static relaxation rate below TC and appearing exactly at TC. The value is actually small, so the internal fields are of the order of 0.1 to 1 Gauss, which is also at the border of what one can measure with muons from the in terms of resolution, because we have to measure time-dependent spectra. And here on the right side, you see some other spectra which we measured some years ago on an even weaker case of time reversal symmetry breaking strontium platinum arsenide. But you clearly see that above the superconducting transition, there is some sort of relaxation of the muon signal as a function of time. But below that transition, there is an increase, and we can measure these kind of signals. As Vadim said, there are a handful of systems, about 20 systems, superconductors, in which we have seen this, or other people have also seen this in with muons. The problem, of course, with strontium ruthenate is since that in the last year, in the last decade, I would even say, this chiral p-wave state has been questioned already by several experiments, and the last one is really the very important experiment by Stuart Brown's group, and also confirmed by Kenji Ishida, that now in strontium ruthenate there is this night shift change or reduction of night shift below Tc, so that it is definitely spin singlet even pairing state. And there were indications for that the p-wave state is not the correct one already during the last decade. And one of the most important already was in 2014, and by many other groups also, that you really have an HC2 at close to HC2 at low temperatures, kind of first order transition and a Pauli limiting behavior. And I don't want to go into detail for time reasons on all the other questions. So it's wise to check if there is really a two-component order parameter. And the idea to do that came from Clifford Hicks and co-workers. That is, if you apply uniaxial pressure, you will remove the degeneracy, for example, of the delta X and delta Y superconductor order parameters. And delta X and delta Y could be Px and Py, but that could also be some other order parameters which have some correlation with the X and Y directions, of course. And of course, we know that this was the expectation. We have an increase of Tc, but on the other hand, the second order parameter is suppressed. So the onset of the coherent state should be at a lower temperature. There should be a second transition into the time reversal symmetry breaking state at applied uniaxial stress. And this was something we wanted to measure with muons, because so far the time reversal symmetry breaking in these systems has only been seen by muons and by the Kerr rotation effects. Yeah, and you already seen that the Tc strongly increases in the experiment. Really, there is here, close to the Van Hove singularity, there's a strong maximum. And we want to see what can we see with muons anti-uniaxial strain if we go through this kind of strain system, uniaxial strain. However, we could not use the small cells which you can commercially buy. We need a much larger sample to get muons onto our sample here. So the beam size is approximately 7 to 8 millimeters. So we need to strongly increase the area and also the thickness of the sample, which means we need to have an in situ uniaxial pressure device, which can give forces up to 100 kilogram or 1000 newtons. And this took really about 5 years to get to the state where we are now. Here you see a sketch of the device. Again, it's driven by piezoelectric cells here. And this whole thing has to go into the dilution fridge, or in our case, the helium-3 cryostat. Now, where's my mouse? Here. And the sample at the end is, I don't know why, I have some problems moving my, okay, now it goes again. I cannot reach the, anyway, at the bottom you see the sample holder, but the problem is that since we have to apply these 100 newtons, up to 1000 newtons, we need to pull on the sample with some device. So some fraction of the sample holder will be in the muon beam also. And to check that we really have a good signal from the sample, we can do transverse field μSR, because in the transverse field, you expect to see the vortex line of the state, and there are predictions from many years ago by Daniel Echterberg that you would see this characteristic distribution of internal fields in the superconducting state. And here on the right side, you see one of these experiments. Above TC, that is a black curve, we have seen the internal field, which is basically the same as the external field. But then below TC, you see this broad distribution here, which takes us in an analysis that we get really 90 to 95% of the signal from our sample and only 5 to 10% from the background of our sample holder. So this now, then we can go to zero field μSR and look for the time reversal symmetry breaking. I don't know where you see my cursor, but.
Yes, it's clear.
Okay, because I don't see it on my screen for some reason. Okay, on the left side, here you see first data for low strains. So here's zero strain, and then we apply some strains on this shoulder where still the TC goes up by applying strain. And here on the right side, you see the data, and you see, for example, that at zero strain, indeed, the black curve here now is an AC susceptibility measurement in situ, and the green data points are the relaxation rates in the μSR experiment. And you see that within resolution of temperature, the onset of the time reversal symmetry breaking is at TC. But then if we go to a little bit higher strain already, you see that as was known already, the TC increases, but as you can see here, the temperature where time reversal symmetry breaking exists is more or less constant. So there is a splitting developing, clearly, even if we go to a little bit higher strain, you see it here, but which is kind of astonishing is that more or less there is no change of the temperature at which time reversal symmetry breaking appears. So the temperature T, TRSB is nearly constant. If one looks a bit more closer, there is some change at low strain, but I don't want to go into details here. So if we go to higher strain, and now if you look here, I have to go very slowly on the left side. So we cross above the Van Hove singularity actually. So here on the top, again, you see the zero strain point, but now we have this very high strain point here. We still have high TC here, of course, now above 3.4 Kelvin. And then still we have time reversal symmetry breaking. But now at the maximum, at one strain point here, which is 0.75 GPa and 0.82 GPa, it looks like there is some reduction of the time reversal symmetry breaking temperature. But still, I want to point out we are above the Van Hove singularity, and there is still time reversal symmetry breaking and no spin density wave or other kind of magnetic order. So we are right now here. But if we go to our maximum uniaxial pressure, which we could apply, which is roughly about 0.85 gigapascal, no, 1.0 gigapascal, sorry, minus 1.0 gigapascal, then the spectra completely change. And here you see the time spectra in the μSR experiment at high temperature slowly relaxing, this as usual. But then below 7 Kelvin, you see the clear development of coherent oscillations of the muon spins. And that means we develop static magnetic order with a large internal magnetic field. And so the internal magnetic field turns out to be now in the order of, at low temperatures, here is the magnetic field as a function of temperature. It's about 5 millitesla. That means 50 Gauss. So it's near definitely a factor of 50 times stronger than any magnetic field which we have seen in the time reversal symmetry breaking superconducting state. Is there still superconductivity? Yes, there are some indications that in the IC susceptibility, we do see that there is an onset of superconductivity at roughly half of the Néel temperature of this magnetic ordering. And we also see some interplay of superconductivity or hints of interplay of the superconductivity with the magnetic order, because this is the temperature below 3.5 Kelvin where the relaxation rate of our muon signal, the static line width, is increasing a little bit more. Nevertheless, I want to point out that since this magnetism is really much stronger than the time reversal symmetry breaking magnetism which we see, in our interpretation, this is a competing state and it's not the same kind of magnetism which appears in the time reversal symmetry breaking. Yeah, the physics of that has been already proposed in different ways. If we approach the Van Hove singularity here, and for example, in this theoretical study, there are different ways to form a spin density wave order by nesting on the Fermi surface in the vicinity of the Van Hove singularity point here. In the theory, it was actually predicted that you should already have spin density wave order below the Van Hove singularity point. That would be the figures A and B in this study. However, we clearly only see the magnetic order above the Van Hove point. And yeah, this is the final phase diagram which we have determined in this study. So we have reconfirmed in our in situ AC susceptibility measurement that there is, of course, a strong maximum in the TC, roughly at 0.6 to minus 0.75 gigapascal. We have this splitting. We definitely observed a splitting between TC and time reversal symmetry breaking, which increases with strain here on this part. And at very high strain, namely at minus 1 gigapascal, we observed spin density wave magnetic order. And in our interpretation, this really competes with the superconducting phase at lower strain. Yeah, what are the consequences for the superconducting order parameter? Well, indeed, we think these experimentally clearly proves that we remove a degeneracy between two superconducting order parameter symmetries with the strain. And one possibility to reconcile this with the spin singlet superconductivity is actually the chiral dxz plus minus ID YZ order, which has already discussed by Clifford an hour ago. And so it has some problems that it has this horizontal line node here. There are other cases of accidental degeneracy states, so S plus minus ID or D plus minus IG. There is no way really to understand why they are appearing, have exactly at TC, that they really have at the same time. So you form in the unstrained sample, the time reversal symmetry breaking exactly at TC. There are some new approaches, which look at local orbital electron-electron coupling by Daniel Achterberg and Carsten Timm and co-workers. And from these, there are several additional order parameters possible. And so these open up the case that indeed there will be singlet superconductivity by degenerate orbital states in strontium ruthenate. Yeah, for us, the next step in our experiments will be to map out the spin density wave phase at high strain and to test this accidental degeneracy. For example, we want to also apply uniaxial strain along 110 direction. And we are, as Vadim already told, on the way in doing studies with controlled impurities via heavy ion irradiation or doping experiments to really explain more about, or find out experimentally more about the degeneracy of these TC and the time reversal symmetry breaking here at 0 strain also, and how we can, if we can manipulate that. With that, I want to thank you very much for your attention.
Thank you very much for your very nice talk. We have time for one, probably, or two maximum questions. Please, any question? Herman, yes, please.
Yeah, yeah, thank you. Thank you for the nice talk. I just have one, because you mentioned that at some point you measured the vortex lattice, or you mentioned the vortex lattice. Did you think about the problem of the vortex core size in this material? Can you say something about that?
I didn't understand it. About what?
About the problem of the vortex core size with mu. Yeah, go ahead.
Yeah, I think there we did not, in these studies under uniaxial strain, we did not have the intensity and the time to really look in this detail to the structure of the vortex lattice. To look at the vortex core size, actually with μSR you can do it, but basically it means that if you look at the theoretical structure here, you really have to determine very accurately the real form of these field distribution. And in our study, this was not possible.
Okay, thank you very much.
Thank you very much. So the aim is that we continue the discussion in the afternoon. In any case, so we have a similar themes, let's say, and we can continue in the afternoon if there are more questions about the topic. So thank you once more, Hans Henning, and let's move to Luke, to the next speaker, who is Luke Rhodes from St. Andrews, and he's going to talk about the dxy orbital, the role of that in the nematic and superconducting state of iron selenide.
Okay, can everyone see me on the screen?
Not yet.
Yes. No? Okay, let's try again, sorry. Sorry. How about now?
Very good.
Perfect. Okay. Hello, everyone. Thank you. Thank you for your attention. Thank you, Joseph, for allowing me to present my work. My name is Luke Rhodes. I'm from the University of St. Andrews in the United Kingdom. Now, this morning we heard a really nice talk by mini-colloquia about the electronic properties and electronic structure of iron selenide in the nematic state. And one of the main questions that appeared to come from this talk was, what was the nature of the dxy orbital within this system, and how was that evolving? So what I want to present to you today is a new theory that we've been developing that can hopefully address this question. And I want to talk about the importance of this dxy orbital on both the nematic and the superconducting state properties of this material. So the work that I'm going to talk about today has just appeared on the archive this morning, and it wouldn't have been possible without Jakob Borka, Marvin Muller and Ilya Eremin at the University of Bochum, and Matthias Eschrig at the University of Griefswald. Okay, so let me just give a brief introduction into the nematic state from a more theoretical point of view. Nematicity is the spontaneous rotational symmetry breaking of a material's physical properties, but specifically due to some form of electronic interaction. Now, theoretically, this can be generated via many different mechanisms, as Amalia discussed this morning. It can be generated via magnetic degrees of freedom, such as in an icing nematic scenario, or it can be generated from electronic degrees of freedom, such as the Pomeranchuk instability of Fermi liquid theory. But the issue is, in real systems that exhibit a nematic state, such as many iron-based superconductors, there's relatively little consensus on what is driving the nematic mechanism in these materials. And this is one of the reasons why so much attention has been placed on the material known as iron selenide, and more specifically, over the last couple of years, the iron selenium sulfur phase diagram. This here is the doping phase diagram as a function of sulfur doping and temperature. And you can see this phase diagram exhibits a large region of phase space with which to probe this nematic state and also its interplay with superconductivity. Moreover, because sulfur is isovalent to selenium, you're not adding or removing any hole or electron carriers when you dope this material. You're simply applying a bit of chemical pressure, which has the effect of suppressing this nematic transition, whilst leaving the underlying electronic properties in the tetragonal state relatively unaffected. And so you can think of 18% iron selenium sulfur as having practically equivalent electronic properties to that of pure iron selenide at about 1900 Kelvin. So over the years, a lot of experimental resources have gone into probing this phase diagram. And what I want to present today is a theory which can hopefully unify many of the unusual experimental results that we are observing. Now, if we want to understand the nematic state of iron selenide, we first have to also address the issue of the multi-orbital nature of these materials. In iron selenide, there are 3 relevant orbital degrees of freedom present around the Fermi level. There's the XZ, the YZ, and the XY orbitals. And if we want to understand how the nematic state affects iron selenide, we first have to understand how the nematic state affects each individual orbital component. Now, for the case of, say, the XZ and YZ orbitals, this is relatively well understood. In the tetragonal state, your XZ and YZ orbitals are degenerate, and that degeneracy is lifted when you break rotational symmetry. But there's a bit more of an open question as to what happens to the DXY orbital upon entering this nematic state. How much this DXY orbital is influenced by nematic ordering. And many theories of the nematic state simply just assume that this term is small and negligible. But today I would like to argue the opposite. I would like to argue that this DXY nematic ordering is just as important, if not more important, than the orbital rearrangement of the XZ and YZ orbitals. And the reason I want to argue this is because it will allow us to address one of the central unanswered questions surrounding the electronic structure of iron selenide. In particular, that is, how does the electronic structure evolve from the tetragonal state into the nematic state? Now, we've heard a lot about this from the experimental point of view from Amalia, but from a theoretical point of view, it's been very challenging to reproduce the experimental data that we are observing. This here is the Fermi surface as measured by ARPES in the tetragonal state at 100 Kelvin. And here is the Fermi surface of a detwinned crystal of iron selenide at low temperatures at 10 Kelvin. So this detwinning simply removes the effect that orthorhombic domains have on ARPES data. So this experimental Fermi surface is relatively, has been reproduced multiple times and is quite consistent with experimental measurements. Here I present to you a cartoon of what that Fermi surface geometry is, where these colors represent the maximum orbital content of the bands. But the question from a theoretical point of view is, how do you go from a system which has 2 hole pockets at the center of the Brillouin zone and 2 electron pockets at the corner of the Brillouin zone, and evolve that into a system which has a elliptical hole pocket, single elliptical hole pocket at the center of the Brillouin zone, and a single electron pocket at the corner of the Brillouin zone? And this has proved to be quite challenging to do. The reason it's proved challenging is because of our current limitation of our understanding of the nematic state. What I mean by that is, if we were to take a model of the electronic structure of iron selenide and apply to it a nematic order parameter that takes into account this rotational symmetry breaking and the lifting of the degeneracy of the XZ and YZ orbitals, then the best possible Fermi surface you can obtain looks like this. And this Fermi surface does capture some of the properties that we observe in the experiment. It captures this elliptical hole pocket you see here, that's this one. And it even captures this peanut-shaped electron pocket that we can see in the ARPES data here. which is this one here. But you may notice, within this theory of nematicity, which purely involves the XZ and YZ states, the model predicts a second large electron pocket of mainly dxy orbital character, which has not been observed within the experimental ARPES measurements. Now, this has been quite confusing and caused a lot of disagreements within the literature, and it's even been given its own name, known as the missing electron pocket. And so we really wanted to understand what has happened to this missing electron pocket within the, comparing the theory and the experiment. So what we did, we went back and we looked at the crystal structure of iron selenide, and we thought about all the possible order parameters that you can write down, which breaks the rotational symmetry of the lattice, specifically the B1G rotational symmetry of the lattice, within a single unit cell involving the XZ, YZ, and XY orbitals. And it turns out there are only 4 equations you can write down. The first 3 involve the XZ and YZ orbitals, as I showed on the previous slide. This first term here is a local nematic ordering, and these 2 terms here are non-local nematic ordering between nearest neighbor hopping anisotropy. But a 4th term that's equally valid is a nematic ordering of the dxy orbital, specifically a hopping anisotropy of nearest neighbor ion atoms in the x and y direction. Now, again, in most theories of the nematic state, this term is considered to be small or negligible. But we simply asked the question, what if that wasn't true? What if this term was actually large? Well, in that scenario, you can generate the correct Fermi surface as measured by ARPES. What you do is you generate a Lifshitz transition of that second electron pocket. You push it above the Fermi level. And that can reproduce the experimental data, not only as a function of the Fermi surface, but also as a function of binding energy. Here we have some ARPES data of the electron pocket around the M point of a D-twinned crystal. This is the Fermi surface of the electron pocket, and these here are cuts along the Y and X direction as a function of binding energy. And this is the first time that such good agreement can be obtained within a model of iron selenide. And it's all because we've included nematicity within this dxy channel. So this is the main idea that we've had, that we think can explain many of the experimental properties. If you assume that nematicity is also strongly present within the dxy orbitals, specifically larger than the nematic term in the dxc and dyz orbitals, then you can reproduce the electronic structure that is observed with ARPES. Now, in the next part of my talk, I just want to talk about the consequences of such a non-local dxy nematic scenario. And the main consequence of this scenario is that what occurs is a Lifshitz transition as a function of both temperature and doping. And this can be experimentally determined. We have naturally, when we thought about this, we went and we looked in the literature to see if there was already evidence for this Lifshitz transition. And it turns out there is, both as a function of temperature and, in our opinion, as a function of sulfur doping. I'd like to focus on this sulfur doping data. This is the quantum oscillations data that Amalia Correa presented earlier this morning, because I would like to show how this data is indeed fully consistent with a Lifshitz transition associated with a dxy electron pocket. So to show you this, what I'm going to do is simply plot the areas of the hole and electron pocket at both the kz equals 0 and kz equals pi states of a model of iron selenide which has been fit to the experimental ARPES data. And then we're going to apply a mean field nematic order parameter term, where 18% is the pure tetragonal state and 0% is the pure nematic state, and see how these areas evolve. What we find is that for a wide variety of the doping levels, very little occurs. these 4 areas that we can see here remain roughly constant with a slight increase. And a 5th area appears due to this inner hole pocket coming back above the Fermi level. But at this Lifshitz transition of the dxy electron pocket, which occurs in our model about 14%, what you find is the presence of 2 new extremal areas from the Lifshitz transition, which sharply increase in size. And this sharp increase in size here would be a signature of this dxy Lifshitz transition. And if you compare this with the experimental data in this MPJ quantum materials paper, although this wasn't the interpretation in the manuscript, if you assume that a Lifshitz transition occurs about 15% sulfur doping, these data points are entirely consistent with a sudden sharp upturn that occurs beyond a beyond this Lifshitz transition. Moreover, this may also be able to explain why recent resistivity measurements have detected evidence of quantum criticality occurring at about 16% sulfur doping when the structural transition doesn't end to about 17–18%. Assuming that these guys got their doping levels correct, then this could just be evidence for the Lifshitz transition. Okay, so in the final couple of minutes, I just want to talk briefly about the superconducting properties of this system and how this non-local dxy nematicity would affect the superconducting state. So what we've done is we've simulated the momentum dependence of the superconducting gap of this model, assuming some spin fluctuation mediated superconductivity. The result is that we obtain a highly anisotropic momentum distribution that has a sign change between the hole and the electron pockets. And this momentum distribution directly reproduces the experimental data as determined by STM and ARPES. Now, this is very exciting because there's theories of the nematic state which only involve XZ and YZ nematic ordering have not been able to reproduce this momentum dependence purely from nematic ordering alone. And so this is really quite strong evidence that what we are, that this dxy nematicity is an important contributor. Okay, now the superconducting gap structure of iron selenide has been extensively studied within the experimental literature. However, it is not yet known how this momentum dependence of the superconducting gap will evolve as you increase sulfur doping and decrease this nematic transition. And so we, in our manuscript here, we have made this prediction. I won't go into the details here, but what we expect is that a majority of the changes will occur at this Lifshitz transition, going from a highly C2 symmetric momentum dependence to a more C4-like momentum dependence will occur at this Lifshitz transition before going into a fully tetragonal state. And again, this hasn't been experimentally measured yet and will be a good prediction for this dxy nematic scenario. Okay, so with that, I would like to conclude. What I presented here today is a model which considers nematicity affecting on not just the XZ and YZ orbitals, but also the XY orbital. And we've shown that this can reproduce the electronic structure as observed by experiment, and it makes a nice prediction that there should be a Lifshitz transition within this phase diagram, which can be experimentally verified. So with that, I thank you for your attention and look forward to your questions. Thank you.
Thank you very much, Luke. We have time for one question. We are running behind schedule, so let's have one question and then we can continue because it's very, very interesting subject in the afternoon. Please, yeah. Rosa, yeah.
Awesome.
Okay, sorry, just a short question. So do you have some way, like for instance with the free energy, to understand why this channel of nematicity should in fact be more favored for the case of iron selenium?
From a theoretical point of view, no. But this qualitatively, this is a more strongly correlated orbital. And therefore, if nematicity is some strongly correlated phenomena, maybe that has a role.
Mm-hmm. Okay, thank you.
Can I also ask a question?
Yes.
I think my question is about terminology and about Lifshitz transition terminology in terms of hole bands appearing or electron bands appearing, because experimentally, as you heard earlier, we see the appearance of the hole bands with sulfur substitution from about 11%, or it could be slightly before. So I think what you're suggesting, either that they appear at the same time, or there are two different appearance of different pockets at different time, and that there will be different transitions, different new carriers appearing.
Yeah, you're completely right. There will be two Lifshitz transitions: this hole pocket one and this electron pocket one. Yes, I completely agree.
And also with quantum oscillation, we suggest that there is something else happening right on the border, which could be a disappearance.
Potentially, yes.
Great, thank you very much. Let's move now to Alireza Bari, who is going to talk us about gap Dirac-Cones and thin film topological insulators. Great. Yes?
Yeah, I'm trying to activate my mouse. But I think something is okay. Can you see my mouse or not?
Yeah.
Something's funny happened. Okay. Can you hear me?
Yes, fine.
Okay. Hello, everybody. I'm going to talk about something is up. Okay. I'm going to talk about the quasi-particle interference in gap Dirac-Coin in thin film topological insulator, and this is work which we have done with Peter Thalmeier, and you can find the detail of these calculations in our recent publication in Physical Review Research. Okay, we know that surface state, protected surface state in topological insulator are given by this kind of the Dirac coin on the surface of the system, and this kind of Dirac coin can be detected via a spectroscopy technique like ARPES, and also with the STM-based quasi-particle interference technique. And since this opposite layer on top and bottom can talk to each other, we know that this Dirac coin can be gapped, and by decreasing of the thickness, this gap become wider and wider in the system. So also this can be this kind of opening of the gap nicely have been seen in ARPES data, for example, in bismuth selenide, which for a system larger, thicker than 6 QL, you can nicely detect this kind of the Dirac coin in the system, and by reducing of the thickness, you see that below 5 QL, this gap become open and become wider by reducing of the thickness as well. So up to now, the only data we show this effect is ARPES, and this motivates us to look at the alternative technique to the system, if it's possible to catch similar data or some more information about the opening of the gap in this thin film. So we look at the quasi-particle interference in the system, and for doing that, we start from the surface state in the system, which represented by this Hamiltonian, which the first term shows the perfect Dirac coin, and the second term represented a warping effect, the system which can represent it in 2x2 matrix with the dispersion of epsilon k of the Dirac coin, and the warping effect can be controlled by azimuthal angle theta k, which is in the k-space. And if you diagonalize this Hamiltonian for a single layer, you will end up with this helical state, which has an opposite helicity on top and bond, lower bound, and is perfect. There is no sign of the gap in the system. But if we include the second layer in the bottom and allow them to talk via hybridization inside of the bulk, then which this hybridization represented by T in this Hamiltonian, you will end up with a 4x4 matrix, and you can move from the base spin basis to helical base, and again you can diagonalize the system, and at the end of the day you can find this state which become gap at the final hopping. So which is represented in the right hand side of the presentations. So also you can look at the dispersion of the system, and for the perfect Dirac coin, you see that it's represented at 0, and by some constant adding to the hopping, you see that this gap open in the system. And also, if you look at the spectral function of the system, you will see that, okay, at 0t, we start from the point, and the spectral function growing, and will end up with the snowflake feature at higher energies. And also in the finite t, you see that the effect of the gap is going to show up at the lower energy, lower than t, which we don't have any spectral functions, and then by increasing of the t above the energy above the t, this spectral function will appear by a small circle and increasing by energy with snowflake features. So now we are ready to look at the calculation for quasi-particle interference. For doing that, first I would like to say some word about the quasi-particle interference, which we know that this is an impurity-based technique, which we know that in presence of impurity, the impurity can scatter the electrons, and as a result of that, the scattered electron can interfere with the original electrons, and it produces a standing wave-like feature on the density of a state on the surface of sample, and this can be detected by STM. And when you look at the Fourier transform of the STM result, this result shows the enhancement at this momentum vector Q. And this is can be represented even in the Born approximations with the convolution of the two propagator at incoming and outgoing momenta. And for example, if you have a normal state feature with the parabolic dispersion, which constant energy contour given by a circle, we expect to see the circle-like feature in QPI as well, but with the momentum with 2 times larger than the original momentum. And also you can detect similar dispersion in QPI with the same fashions. So in principle, for our model, we just need to find the total Green's function, and by looking at the imaginary part of that, we can detect the modulation of the density of the states. So in this Dyson diagram, which we need to solve, you represented the interaction of the impurities, and these impurities can be either potential impurity or magnetic impurities, and as a result, for such a system, we have a propagator in 4x4 matrix, and in the spin representation, it can schematically represented as this with the scattering of the electron on top, with the same propagator on top and going out, or coming with the electron on top and going to the bottom layer and scatter there and going back to the top layer of the sample. So in principle, this is the thing which we need to do, but we should recognize that, okay, in all calculation, everything is written in helical basis. Therefore, we need to transfer everything from the base spin basis to helical state basis. And this is a little bit technical, and you can find the detail in the paper, but at the end of the day, you can find the pack equation for that, which controlled by these Cohen's form factors, and there's 2/3 of them is represented to the activity on the top layer, and 2 terms in the bottom represented to the scattering from the top to scattering from the bottom layer, and therefore is proportional to T squared. So we are ready. We can just run the calculations and you look at what we can learn in quasi-particle interference pattern. So in the left hand, we have the spectral quasi-particle interference pattern for zero hopping, and you see that it starts at from some kind of the drop-like isotropic feature at the low energies, and by going to the lower higher energy, it starts to show some snowflake feature, and this snowflake feature become wider and wider by going to the higher energy. And this is exactly which we expect, which we saw also in the typical topological insulator. Now, if we go to the higher hopping, you see that the effect of the gap appears in the system at lower energy, which energy is less than T. We don't have any spectral function, therefore we don't see any trace of the QPI. But if you go to the higher energy, then you see that it starts from the drop-like feature and shows a similar fashion at the higher energies. So also, we can look at the dispersion of the QPI feature. In the left-hand side, I show the dispersion for original model for 2 certain momentum direction from 0, 0 to 0 minus pi, or 0, 0 to 0 pi direction. And in the right-hand side, you see that, okay, if I run the QPI calculation, nicely, you can see the similar dispersion also in the QPI feature. And the only thing is that, okay, the momentum in the dispersion is by a factor of 2 wider. So you see that by going to the higher hopping or increasing of the gap in the system, this gap also appears in the QPI feature and can be detected in the future experiment. So in the second part of the presentation, I would like to say some word about the thickness dependency of these hopping parameters. And we know that from the paper by Ismar that by starting from the simple K.P parametric model in the bulk and including the boundary condition of the topological insulator on top surface and lower surface, we can see that these hopping parameters show 2 different features. First, exponentially decaying by increasing of the thickness, and the second part is also show some kind of the oscillatory behavior. So if you look at the bismuth selenide data, for example, from the ARPES, you don't see any oscillations, and that means that, okay, still we are not in the regime that thickness showed any oscillation in the hopping. But for the case of the bismuth telluride, we expect to see more oscillation in the system. So for this reason, I catch the first result from the bismuth selenide from the ARPES data for the hopping parameters, and I run the calculation for QPI, and you see that, okay, we see certain change, but mainly is that, okay, for the higher hopping start from the drop-like feature, and this drop-like feature by increasing of the hopping the distance by decreasing of the thickness, show the a smooth decrease in T. Therefore, the QPA feature also smoothly changed to the snowflake feature. And but for the case of the bismuth telluride, since we don't have still any ARPES data or other experimental technique to detect, to check the fitting parameters, but from the theory, we know that we expect to see more oscillations, and I catch this kind of the fitting, and then I run the QPA calculation for same system, and we see that okay, now is perfectly show the oscillation in the QPA feature from the drop-like feature to a snowflake, and also the intensity of the QPA is start to change by increasing or decreasing of the thickness. So that's it. I just want to conclude that okay, for the first time we run the QPA calculation for the topological thin film system, and in comparison with the original ordinary topological insulator, this system becomes gap, and this gap appears also in the QPI feature, and we expect to see nice gap dependency in future experiment. So by that, I would like to thank you for your attention.
Great, thank you very much. So please, any question on Alireza's talk? In any case, we are going to have a session in the afternoon, so basically we can continue this with topological insulators. There will be another pre-recorded talk there. And given that we are running out of time, and our last speaker is patiently waiting from in Boston, let me introduce him. The next talk will be given by Hiroki Isobe from MIT on high order Van Hove singularities and correlation effects, a work that was done in relation to twisted bilayer graphene and the supermetal. So Hiroki.
Yeah, thank you very much for the kind introduction. I think you can hear me and you can see my screen. Okay, so first of all, I'd like to thank the organizers and for this nice opportunity and this great conference. It is unfortunate that we could not meet in person, but I hope everyone stays healthy in your own place. So my talk will focus on topology of Fermi surface, Van Hove singularities, and related electronic properties, mostly focusing on two-dimensional or quasi-two-dimensional materials. So many of the speakers and attendees and organizers have contributed to this field, and I cannot show all references that they contributed to, but I list a few of them. And one famous example of Van Hove singularity in two dimensions is discussed in cuprate materials, where we see Van Hove singularity at zone boundaries, 0 pi and pi 0. And more recently, Van Hove singularity and related effects have been reported in monolithic graphene, and many discussions have been made even in this session about the strontium ruthenate. So let me first focus on strontium ruthenate that many speakers talked about in this session. So this is one experiment under uniaxial strain to this strontium ruthenate, where by applying a strain, we see a touching of Fermi surface at the zone boundary around like this. And with that, they also, corresponding to that, they also observed the enhancement of TC to superconductivity, which is shown like here. In strontium ruthenate 214 material, we see a touching of two Fermi surfaces at zone boundary, which gives rise to a divergence of divergence in density of states corresponding to accompanied by the Van Hove singularity. And this log divergence is universal in two-dimensional materials with saddle point singularities, but more like exotic phenomena happens when more than two Fermi surfaces touch at a point. So, for example, in this example in biennial graphene, three Fermi surfaces touch at a point, and this results in a stronger divergence on log. In this case, this gives rise to a divergence with the power of -1/3. And when four Fermi surfaces touch at a point, then this gives a more stronger divergence with exponent -1/2. Okay, so let me change the top. Let me look at different material twisted biennial graphene. And this material, 2 years ago, MIT group reported superconductivity and correlated insulating behavior, and this like exotic material. And this material is made of simply two graphene sheets, but a little bit of twist relative to each other. And other groups have reproduced the results of superconductivity and correlated insulating behaviors, and even more, there isn't a report of like anomalous Hall effect with some magnetism in this material. And this graphene is a van der Waals material, so there are degrees of freedom and stacking layers. And even other systems like tri-layer graphene on top of hexagonal boron nitride substrate, or double bilayer graphene that is made of two sets of bilayer graphene, but the relative twist of these two layers. And even for those systems, they observed superconductivity as an correlated behavior in this electronic system. Okay, so let's look at Van Hove singularities in this material. So this is a scanning tunneling spectroscopy measurement done for twisted bilayer graphene. And we see clearly Van Hove's density of peaks from corresponding to Van Hove singularities. And the separation of two Van Hove singularity varies depending on the twist angle. As we make the twist angle smaller and smaller, we see a bandwidth becomes also smaller, and this enhances the correlation effect in this in this material. Okay, so this this like small narrow bandwidth happening in twisted bilayer graphene is actually reported theoretically by Bisterton and Alan MacDonald in 2011. They calculated the band spectrum using the continuum model, and they defined, and at a certain twist angle, they observed very narrow bands that occurs near zero energy at Fermi level. But as we have seen from a spectroscopy measurement, this band is very flat, but not exactly flat. Bisterton and MacDonald defined term this like special angle as magic angle, and they define magic angle as the twist angle where direct velocity vanishes. But as we have seen, the bandwidth is not exactly flat, even at this so-called flat magic angle. So instead, we try to look at the Van Hove singularities and examine how they change by tuning the twist angle theta. And from this perspective, we want to redefine the notion of magic angle. Okay, so let's again look at a continuum model for twisted bilayer graphene and change the twist angle to see how Fermi surface topology changes. At relatively large twist angle of 2 degrees, we see a simple like triangular Fermi surface in this hexagonal boron zone. And if we make the twist angle small, say 1.50 degree, then the Fermi surface changes topology, where we see instead of one crossing here, we see two crosses of Fermi surface and one energy maximum surrounding this like small pocket here. And we can clearly see the change of Fermi surface, and this by changing the twist angle theta. That means that there is a critical twist angle where between those two different topology. And at this critical angle, we see a tangential touch of two Fermi surfaces. And at this twist angle, we call the Fermi surface shape at this critical twist angle, we call this Fermi surface as a high order saddle point. So let me more simplify the Fermi surface topology by looking at this Van Hove point. And we can write down the effective model around the Van Hove point based on the symmetry around at this point. And for a larger twist angle, we see a single cross. And for small twist angle, we see two crosses and one energy maximum. And at the critical angle, we see a tangential touch of two Fermi surfaces. And one may ask, what's the consequences of this high order Van Hove singularity? So again, we look at this effective model near this band touching point, and at the critical angle theta c, we don't have this second term in the right hand side of this equation. And without that term, we can establish a scaling invariance in this energy dispersion, which has this form, like this form. And based on this scaling invariance, we can directly find that this leads to a power law divergence in density of states, as we have seen in the multi-criticality of the Fermi surfaces and the introduction part. And this has another interesting feature, which is a asymmetry of the density of states on the electron hole side. So usual log divergence accompanying the saddle point in 2 dimensions have symmetric divergence of density of states and both electron hole side. But for this high order Van Hove singularity, we can see asymmetry of the density of states on the electron and hole side. Now we see how high order Van Hove singularity appear in real materials, twisted graphene. So we try to fit the SDS data using our high order Van Hove singularity density of those spectrum for high order Van Hove singularity. And this is the fit to the experimental data. And this circles are from SDS measurement, and this solid lines are our theoretical fit. And we can fit very nicely at the around the magic angle 1.1 of the experimental data using the high order Van Hove singularity. And we also see the asymmetry of the electron hole side. And for the model of twisted graphene, the factor of the asymmetry is actually square root of 2. And this is like a log plot corresponding to the Van Hove peak and the electron side of the peak. And we also see a ratio of square root of 2, which corresponds to our theoretical estimate. Okay, so far we have discussed about non-interacting features of related to Van Hove singularity or high order Van Hove singularity. And the next question is, what happens to a high order Van Hove singularity when we consider electron interaction effect? And our answer is supermetal, that we define as a electronic metallic state with various divergence susceptibilities, but without any long-range orders. And having a density of state, a divergent density of states, actually has two competing effects. So divergent density of states leads to divergent non-interacting susceptibilities, such as magnetic susceptibility or density compressibility or specific heat. But on the other hand, large density of states strongly screens the electron interaction, so that the effect of electron interaction is not clear without any real theory calculations. Okay, so let's use a slightly different model, but has the same same physical feature as the one for twist about graphene. Instead of twist angle, we have a tuning parameter lambda here, which corresponds to tuning the twist angle and twist about graphene. And by changing this coefficient lambda, we see a similar topological transition of Fermi surface. When this lambda is positive, we have single cross of Fermi surface. And when lambda is negative, we have two crosses and also one maximum. And between them, we have a criticality where we have power law divergence of the surface state. To realize this criticality, we need to tune chemical potential and also a single parameter lambda here, which corresponds to controlling twist angle theta, or strain in strontium ruthenate. The simplest thing for to consider electron interaction effective to mean field analysis, we add contact interactions to this R Hamiltonian of this form and do mean field calculation. And this is a mean field diagram, a mean field phase diagram for magnetization. And this region with blue colors corresponds to the region with finite magnetization. At the critical point where with the chemical potential is 0, even the infinitesimally small interactions drives the system to ferromagnetic state. And away from the criticality, we need finite coupling constant to make the system magnetic. And this phase boundary is actually corresponds to just represents the Stoner criterion for the first order transition to magnetic state. But actually, there are several caveats or problems in this mean field analysis, particularly near critical point with chemical potential 0. At this point, as I said, even the infinitesimally small interaction drives the system to ferromagnetism. But this in this analysis, we completely neglect the effective fluctuations, and this effective fluctuation is large because we have very large density of states. So this like first order transition with infinitesimally small interaction at this critical point is actually an artifact of the mean field analysis. So we need to improve them. So to go beyond mean field analysis, we did algae analysis. Just for theoretical purpose, we generalize the energy expression like this form, but it looks a bit complicated, but the essence is very simple. So we have a -1/4 exponent to the density of state divergence, but we just replaced 1/4 by a small parameter epsilon. And this epsilon is actually the control parameter in this theory. And on top of this like power law divergence, the energy dispersion, we consider contact interaction to see what the interaction effect is in this electronic system. Okay, so this is just a nutshell for algae analysis using energy shell algae scheme. So first we define an action or theory or model at a certain energy lambda, and we integrate out the high energy mode, which is described in like darker color region in this figure. And then we have a new theory with a different cutoff lambda over b. And we need to rescale the theory back to make it the theory have the same energy cutoff as the previous one by rescaling momentum and other fields like this way. And this rescaled model have the same cutoff, but due to this rescaling, we have different coupling constants or different fields. And discussing this like how the coupling constant changes is the purpose of algae analysis. And here I define L as log of B to describe the measure of this like to describe the energy scale of this theory. Okay, so let's look at RG analysis to one loop order first. So this is the result of one loop analysis, one loop RG analysis, and this is RG equations for a chemical potential mu and a coupling constant G. And this, I added bars to those quantities to represent those dimensionless quantity, dimensionless parameters. They are made dimensionless by using the cutoff energy scale lambda here. And from those two RG equations, we can draw RG flow diagram shown on this, shown on the right. And actually, this RG equations have exactly the same form as the 5-4 theory for ferromagnetic phase transition. I mean, that theory that describes the transition between the paramagnetic state and the ferromagnetic state. And but the key difference is that the previous theory for ferromagnetic phase transition described the bosonic theory, whereas our theory is for fermions or electrons. But still, we see a analogy between the analogy to the bosonic 5-4 theory for ferromagnetic phase transition, but different correspondence. So we have chemical potential in our ferromagnetic theory, which corresponds to temperature, and for the theory of ferromagnetic phase transition. And we have the coupling constant. This is in common for both two theories. And we have non-trivial fixed points, as we have seen for Wilson-Fisher theory for 5-4 theory. And this non-trivial fixed points also appears in the ferromagnetic theory. And this non-trivial fixed point is called the Wilson-Fisher fixed point for ferromagnetic phase transition. And the line that connects the non-interacting fixed points at the origin of this phase diagram and the interacting fixed points. And along this line, we have we can see a scaling invariance in the system. And actually, this scaling invariance is critical to the critical behavior of the system. And scaling invariance protects the divergent density of states along the line, which was given originally by divergent density of states. But at the same time, scaling invariance prohibits any long-range order, because with scaling invariance, we cannot establish any long-range order. And as I discussed, as I said, for to realize high-order Van Hove point, we need to, the criterion for this critical behavior is the same as for high-order Van Hove point, because the critical line, the scaling line, is the line that connects the non-interacting point and interacting point. So to realize this metallic critical behavior, we need to tune the chemical potential and also a single parameter lambda corresponding to twist angle theta, twist angle, and a twist biographian, or maybe a uniaxial strain and for and Strontium ruthenate. But we have additional parameter coupling constant G here, but we need to tune this because we have a stable flow along this coupling constant direction. And actually, this is a supermetal, what we define to describe this critical metallic behavior. So again, we define a supermetal as a critical metallic state with various divergent susceptibilities, but without any long-range order. And we have competing effects due to divergent density of states along this critical metallic line. And we have divergent density of states leads to divergent non-interacting susceptibilities, which remains divergent as I discuss later. But still, we have a strong screening of electron interactions, and actually, this strong screening is exactly the key to realize the stable fixed point at finite coupling constant, because strong because we have screening effect in electron interaction. Even though the electron interaction is there, we can find a stable fixed point at a finite coupling constant. Okay, and one additional interesting feature of this supermetal is that this is actually a non-Fermi liquid at the stable fixed point. And we only show the results for one loop RG calculation, but in order to prove that this is non-Fermi liquid, we need a two loop calculation, which I do not show in this talk because it's too complicated. But I just want to say that the anomalous dimension eta is proven to be finite from the two loop RG calculation. Okay, so let me just look into how the phase diagram looks like, combining the results of mean field and RG analysis. So we can argue that mean field analysis is more or less valid when the chemical potential is away from the critical point where the density of states is becoming smaller and smaller. But we need to apply the results from RG analysis to take care of the fluctuation effect, particularly near the critical point with chemical potential 0. So by combining the two results, we get the phase diagram like this. So when the coupling constant large, we get ferromagnetism, which is the same as the mean field analysis. But when the chemical potential is small or coupling constant small, Fermi liquid behavior survives, and whole Fermi liquid and two Fermi liquids are separated by the scaling invariant line, and along this line we see a critical metallic behavior, a supermetal behavior along this critical line, and we have a stable RG flow toward this interacting fixed point, which we prove to be a non-Fermi liquid. Okay, so once we find a critical behavior, one may wonder how the scaling properties are along this scaling invariant line. So we can consider relevant perturbations like chemical potential, magnetic field, or superconducting coupling order parameters on this scaling invariant line, and we can calculate the scaling relations using from this scaling properties for free energies. And those are results for scaling exponents for those physical parameters like compressibility, magnetic accessibility, specific feed, and superconducting accessibility for S-wave pairing. Although this looks a bit complicated, we can argue physical consequences or more simpler way. So at the non-interacting fixed point, without any interaction, all those physical quantities diverge with an exponent minus epsilon. This just reflects the divergent density of states at the non-interacting electronic system. But the interacting fixed point to one loop order, compressibility, magnetic accessibility, specific feed diverges in the same way as the non-interacting fixed point. But there is a suppression of superconducting accessibility. The intuition for this suppression is actually very simple because we have finite repulsion at the stable fixed point, so that the finite repulsion kills the tendency towards the superconductivity. Okay, so we have established the interacting supermetal as a non-Fermi liquid, and there are two simple ingredients for a non-Fermi liquid. One is the power law divergent density of state, and this accompanies a scaling invariant Fermi surface. And the other ingredient is the contact interaction. This is a local interaction and the real space. We have two remarks regarding this interacting supermetal. The advantages over other theories for non-Fermi liquid. So one is that we can do a controlled analysis relying on the small control parameter epsilon, which corresponds to the exponent of the density of state. Because we have a small control parameter epsilon, we do not need any local interaction mediated by gapless boson that appears, for example, in Hertzsprung-Smolia theory for quantum criticality. And the other advantage is that we don't have any, Kohn-Luttinger mechanism towards superconductivity, because Kohn-Luttinger mechanism relies on the 2kF singularity, which naturally arise with the Fermi surface or circular Fermi surface, for example. But we have a scale invariant Fermi surface, so we do not have any length scale, so that we don't have like 2kF singularities, which prevents the superconductivity from the Kohn-Luttinger mechanism. Okay, so let me summarize my talk. So in the first part of my talk, we introduced the high order Van singularity from a continuum model of twisted by the graphene. And we show that we redefine the magic angle as the critical twist angle, where we see a power law divergent density of states instead of a log divergence at a subtle point in two-dimensional electronic dispersions. And we need to tune only one parameter, which is, for example, twist angle or uniaxial strain or pressure to realize high order Van singularity. And the latter part of my talk, I introduced the new notion of supermetal with various divergence possibilities, but without long range order. And we discussed in this section, we discussed the electron interaction effect near the high order Van singularity. And we established an analogy to the 5-4 theory in the Fermionic system. And we show that the interacting supermetal is actually a non-Fermi liquid, and we can do a control analysis relying on a small control parameter epsilon. And lastly, we want to acknowledge my collaborators Liang Fu and Noah Yuan. With that, thank you for your attention.
Great, thank you very much. Thank you very much, Hiroki. Questions, please? Any questions?
I have a question.
Yes.
Where exactly does the smallness of epsilon figure into the analysis? Like, could you expand on it a little?
Oh, okay. So I didn't show explicitly the RG equations, but we can expand RG equation using small epsilon, and this the small epsilon, for example, appears and like question here, and yeah, and this control the theory, which appears from the electron dispersion, and this epsilon corresponds to the density of state.
Yeah, so okay, you're doing a small epsilon expansion, RG.
That's right. That's right.
I've got one question related to twisted bilayer graphene. So have you associated the filling? So basically they see the different phases around integer filling fraction 1, 2, 3. Have you associated, because it's always my point that it's more important to see where Van Hoff singularities are, and second step is related to the filling. But have you done this to associate the Van Hoff singularities with filling?
Right. Yeah. Thank you for pointing out. This is actually a very good point. And yeah, to be honest, when we did this analysis, we only know that superconductivity appears only near half filling, and actually the appearance of this like Van Hoff singularity is very close to half filling, and so that we may argue that the superconductivity near that filling may be related to this Van Hoff singularity, but so far it's not straightforward to apply this Van Hoff scenario to other integer fillings.
Yeah, I see the point. Yeah, and the other, I mean, probably in twisted bilayer graphene, it's this analysis. I mean, it's fine in the sense that you have this scale invariant Fermi surfaces, but in other real material, in other materials that more complicated, more bands, probably everything will be important in my view, in the sense that you have then scattering from other parts of Fermi surfaces that are there. So basically in Strontium ruthenate, certainly this is something that is happening, that other parts also play a role, and therefore Kohn-Lattinger, for instance, superconductivity may be seen elsewhere.
Yes, yeah, I agree with you. So this scenario for supermetal only survives when we have single such a Van Hove point, but with multiple points, multiple Van Hove points talk each other, and that leads to some electronic instabilities, or like superconductivity, or like CDW, or some like insulating state. Yes.
Perfect. Any other question?
Just to return briefly to the epsilon parameter, right? It's not like is it like you're doing some sort of a dimensional regularization using epsilon, or is that not the way in which you use epsilon?
Sorry. What regularization? Could you repeat that again?
Dimensional regularization. I mean, like, I'm trying to understand like how exactly epsilon might feature in the RG. Like, it's not like a dimensional regularization or any other. Like, it's. I mean, like,
okay, so
in the RG analysis, do you use dimensional regularization or something? Do you have any divergences that prop up that you try to cure by, I don't know, some technique like dimensional regularization or?
Right. So actually, in our paper, we did both energy share RG and also soft energy cutoff scheme, which corresponds to like sort of polyvalence regularization, but yeah, it's like sort of close to Feynman regularization, but because although the two details, so I didn't explicitly show in my talk. So I would really appreciate it if you could refer to our paper to detail.
Sure, thanks.
Thank you.
Great, thank you very much. Thank you all the speakers very much about, I mean, it was a very, very nice session. And let me remind you of this afternoon's session at 5 o'clock, and also tomorrow morning. Thank you very much.
Hi, Professor Joseph.
Hello.
Hi. So, okay, let me. Okay. Perfect. Hi. What's everything? I'm going to stop the recording.
Sure. Everything went smoothly. I mean,